So welcome to the second day of the school. So it's my pleasure to introduce Heinloth Jochen, and who is going to talk about modular spaces of Higgs bundles.
Yeah, thank you very much for the introduction, also for the invitation to give a mini course here. So I kind of intentionally left the title a bit vague. There's some story to it which is related to the fact that this is a postponed summer school that in between changed topics, and my suggestion to also change this particular speaker was discussed, but well, okay. So I'm here, and so I until a few weeks ago, I mean, I wanted to think about what I want to talk about. So it's on Hodge theory, and so I thought, okay, the thing I can talk about, which is a bit related to Hodge theory, is moduli spaces of Higgs bundles. So I had some plan what I wanted to do, and then 2 weeks ago, my plan kind of changed a little bit, because there was sort of one of my favorite conjectures on this problem appeared to be solved on the archive. Last week it became worse because there was a second proof, and okay, so I changed a little bit my plan, and so my plan is to first today to try to advertise this conjecture, because I think it fits well into Hodge theory, and then in the rest of the course to try to explain a little bit what we know about the geometry of the spaces, and kind of give some glimpses of what structure on this cohomology, on the symmetries that we know in these spaces, actually allowed this progress. Not that I completely understand it, but we will see sort of the geometric thing might at least be useful for you in case you want to read the proof. So that's the plan. So today, my first lecture will be something that I might call Introduction to the P equals W conjecture. So it will just be a story. Well, should I call it conjecture of phenomenon? So, okay, so. So to start with, I mean, sort of this moduli spaces of Higgs bundles enter Hodge theory in two ways. I mean, first there's Simpson's point of view, that they themselves give you an example of what he calls a non-abelian Hodge correspondence, which is a beautiful geometric picture I will talk about a little bit, but which is in kind of conflict to what Bruno says, that Hodge theory is meant to take a variety and replace it by a linear object to make it simpler. So non-abelian Hodge theory takes your variety and replaces with a different variety that you also do not understand. So that's, I mean, I'm exaggerating. Of course, you gain information by this, and sort of this also had beautiful applications like restricting what fundamental groups can appear in projective varieties and so on. But still, it's a complicated variety that we don't, I mean, it's a bit more linear than the variety we started off with, but not in such a way that we start. But there is a second aspect of this, namely it gives you a class of manifolds that have two different algebraic structures. And so both of these algebraic structures give you a Hodge filtration on cohomology, a Hodge structure on cohomology, and it's kind of, they are very different. And it's the interaction of these two structures is something that this P equals W conjecture is about. So before starting out with this general thing, let me just start out with this stupid example that you have to keep in mind. Maybe you know it already, that that you can completely understand how such a thing may appear. So the stupid example of a variety that has two different algebraic structures is the following. You start out with an elliptic curve, or, well, could take any abelian variety, but takes a cotangent bundle of an elliptic curve. So we are over the complex numbers because we are in a school on Hodge theory. So the E is an elliptic curve. The complex numbers. Then because this is an abelian, it's a group, so the cotangent bundle is actually trivial. So that's isomorphic to C times the elliptic curve, which is, well, an elliptic curve you can understand as a complex torus. And so now I do the thing that algebraic geometrists hate or love, depending on what you do. So if you look at this from a topologist's point of view, then this is, of course, stupid. So this is just what you did is it's R2 times S1 squared. Now, R times S1, the real numbers times the circle is the punctured plane. So this is C star squared by the logarithm and the angle. So now you found a variety that has, this is also an algebraic variety. So this is an affine variety. And the other one is not at all affine. And if you look at the cohomology, so you get two Hodge structures on the cohomology of this space through this isomorphism. And what are they? Well, for the cohomology of the cotangent bundle, well, the cotangent bundle doesn't really matter. You just find the cohomology of your elliptic curve back. And we saw yesterday, we know what this is. So this is, so how should I write it? So in the terms of yesterday, so you have H0, which is Q, then you have H1, which is and you have H2, which is has Hodge weight 1, 1 only. And so this is, they are all of these gadgets are one dimensional. Well, I should, sorry. And now the cohomology of the torus, well, we saw, yes, so the cohomology of C star, you know, that is, well, H0 and H1. You also find a one-dimensional space, but this is of weight 1, 1. This is something that we saw in Javier's talk yesterday, so that the cohomology has this 2 pi I inside, if you want to do it with a Hodge structure. We'll comment on this in a second, a little bit more. So again, this is H. So the dimensions are 0, but now something strange happens, that in cohomological degree 1, you get a Hodge structure of weight 1, which is 2-dimensional. And in degree 2, you get a Hodge structure of weight 2, 2, which is 1-dimensional. And so the Hodge structures are very different. So maybe I should recall this. So this is what's called, so it's a mixed Hodge structure. And this is, it's called a pure Hodge structure. Maybe I should, so this is a pure Hodge structure because it is the cohomology of a smooth projective variety. And it's a Hodge structure in the sense that Bruno explained, so you have a filtration. So maybe I should recall you to the linear, maybe because mixed Hodge structures weren't really introduced and they show up here in a kind of essential way. So you should recall that maybe if you for any algebraic variety of the complex numbers, the cohomology with complex coefficients carries a mixed Hodge structure. Maybe you should write it like this so that It's always the integral cohomology, and then once you tensor with C, you have some filtrations. So the one filtration, okay, so has a filtration. So increasing filtration. And then there's Hodge filtration. Such that once you restrict to the graded pieces of this W, the Hodge filtration becomes a pure Hodge structure in the sense that Bruno discussed yesterday. And how is this done? Maybe we don't need too much about this for the moment, but say that if X is smooth, so this was introduced by de Ligne in a famous series of articles. So if X is smooth, but maybe just to, if you have not, I mean, hopefully you have seen this before, but if not, then maybe the following could be helpful. Then you can compute this filtrations by comparing the cohomology of X with the cohomology X bar of a nice smooth compactification. Questions or critique? All is very welcome. So for example, so the first thing to keep in mind is suppose you have X inside a smooth projective variety, and the complement is also smooth of codimension, say C. Then you get a Gaussian sequence. Yeah, maybe I like to call it like this. And so you get a Gaussian sequence where this strange sheaf, if you have not, so this is just the cohomology of, now I have to think. So it's this map has a degree in cohomology, and it's helpful to write this state twist here. Well, this relates the cohomology of X to the cohomology of the X bar, which already has a Hodge structure, to the cohomology of Z. So this is the cohomology of Z. And now this sequence, all the natural sequences you know from cohomology will preserve your Hodge structures. And so by staring at this, you could ask yourself, okay, in the Gaussian sequence, there's this strange shift in cohomological degree, and what should this actually do on cohomology? And well, the way I can remember it best is the following: that if you have a smooth variety, you include it in its completion. You can restrict the Gaussian morphism. Once you compose with a composition with a restriction to Z, this composition is the cup product with the Chern class of the normal bundle. Now, Chern classes have weight twice the dimension, so this composition should be a cup product with a Chern class. So this thing should change the Hodge weight by C. And so this tensor of C, so this bracket 1 is, please take the top cohomology of B1 and tensor with it as a Hodge structure. And if I write tensor C, you do this C times. So and this gives the filtration, gives the Hodge structure. on H star of X. And now there's something, so, and now in general, you can always choose a smooth compactification such that the complement is, say, a normal crossing divisor. And then inductively by this procedure, by taking out the iterated intersections of your divisor, you get a Hodge structure on your variety. Now, there's one thing that's interesting to remark. Namely, you can look at the image of this complete thing and the image of your cohomology. Well, if all your morphisms are compatible with your Hodge structure, then then you can, what did I want to say? Right, then you can see that, well, if you look at this long exact sequence, if you look here, then this is an odd shift of the cohomology of your smooth proper variety. So here the Hodge weights, the weight parts that can appear on the right-hand side are different from those that can appear on the left-hand side. And namely, these that appear here can never sort of come from a projective variety, but they appear in the wrong filtration step. So there's what's called the pure part of the cohomology, which is the cohomology classes in H star X that actually have the Hodge weights that they should have if they were coming from a projective variety. And these are just the image of the compactification. And the funny thing about this observation is, so if you want to have a class, an Hn, that has Hodge weight n, it has to come from the left-hand side. It cannot come from the right-hand side, and vice versa. And so the image of this cohomology of the filtration doesn't actually depend on the compactification, which is something that's non-obvious from a topological point of view. Oh, yes, there's always the, okay, so I'm, yeah, yes, so that I'm all, well, no, I mean, so I think if the, so that, yeah, okay, so maybe I should take the linear convention. So the problem is that with this, then this convention is also wrong, right? So but yes, so I'm okay. This is even recorded, yes. So okay, so I can have no chance, but so I have to do this. Yes, right. Okay, there's no way to go about. But so for some reason that is always, yes, yeah, for reasons that are unclear to me, sort of the cohomology of weight 2 is, yeah, there's some minor signs in the convention that I cannot understand and that I find personally confusing. But there's certainly some good reason for it. I don't know. So, but the upshot is, so upshot, so to remember the image are exactly the cohomology classes of H star X that occur in the expected Hodge weight. So the first step of this filtration somehow, and if you go and then you continue, and this is something you see in this C star. I mean, the C star, it's a bit ridiculous because you see the compactification, is P1. So the only class that survives the restriction to this is the class in degree 0. But the class in degree 1, you see, it comes from if you look at the Gusen sequence for P1 for this thing, it's easy. So this has an H2, which, since this does not have an H2, this class has to vanish here. So it has to come from this thing, but this is the direct sum of twice the cohomology of a point, because these points are equal. I mean, the thing that comes from the H1 has to have the same Hodge weight than the image here. So that's how this Hodge structure coming from H2 of P1 is sort of transferred to something in H1 of Gn. So it's called the pure classes. Good. Okay, so that was an aside that hopefully will appear again. So let's go back to this strange example. Back to the example. Is not entirely random. This is not random because you see the C star squared. This is actually so where do we see two C stars? That's the fundamental. I mean, this decomposition on the right hand side comes from the fundamental group of my curve. So I can identify this with homomorphisms from the fundamental group of my elliptic curve to C star. And this is actually the same. So now I see an analytic reason why this variety could appear. So this as a set, I could view it as pairs LD, where L is a line bundle on E. And yeah, now I have to do the weird thing. There's a flat connection. So line bundles, so the Riemann-Hilbert correspondence tells me that line bundles with flat connection are the same as representations of my fundamental group. And so here maybe the flat connection, I mean, usually you would write the flat connection as an action of the tangent vectors on your bundle. And I just tensored it on the other side as is convenient in the Higgs bundle world. And this is the Riemann-Hilbert correspondence. And this is actually an analytic isomorphism. So this is less strange than this seemingly random choice of the splitting. And this has the advantage that this already has a forgetful map to the pic 0 of my curve. Because if you want to have a flat connection, then you better have degree 0. Okay, so this space on the right-hand side already has the fibers, this is a bundle for the global sections E comma omega. If you have a connection, you can add differential to it. And actually you can, because this unfortunately doesn't have a 0 section, it's just a torso, but you can deform this. So this is the right-hand side. Bundles plus connection can be deformed into the cotangent bundle of your elliptic curve. And there's several ways to do this. So classically, I think people write it like, so this is due to Simpson probably. So I guess this isomorphism was, I mean, I'm not sure where it appeared first, but I mean, I think maybe it first appeared in an observation of Serre, who found these varieties without writing them like this. So if you want exercises, it's a very nice exercise to write down this total space. I mean, think of an elliptic curve. How do you actually find something that is a bundle for this one-dimensional vector space over it that does not have a 0 section? How would you construct it geometrically? is a nice exercise to think about. And it's not, I mean, it's really an exercise. You just have to look at it from the right perspective, and then it's not hard to see. And so there's two versions. So maybe one version is to write down, so what's the connection data? Connection. So this is a map that if you take a section and multiply it with a function, well, it doesn't quite multiply, but you have this Leibniz rule, right? So that it's a bit unusual to write it in this way. So in differential geometry, you will always do the other, but that's the way to do this. And then what people usually do is say, well, look at morphisms from between these bundles that satisfy this Leibniz rule up to a factor or lambda in C. That's what Simpson calls a lambda connection. And so for lambda equals 1, you get connections. And for lambda equals 0, get a section. Get a holomorphic map. So the map of OC modules. Which is your tangent bundle. And again, this is not entirely strange. Even for an algebraist, this is a kind of a natural thing to do, because what's a bundle with a connection? It's a module under the algebra of differential operators. Now, differential operators are a graded algebra, and the associated graded is the symmetric powers of the tangent space of your thing. So whenever I have a module under a graded algebra, I can also always degenerate the algebra to its associated graded algebra. And that's what's happening here. It's just written down in this one way. And because I'm considering curves, this flatness condition never appears because there's no space for the curvature. Okay. Good. So now the Simpson correspondence, or non-abelian Hodge correspondence, says that this picture generalizes in an amazing way. Yes. Yes. So this is what happens here, right? So in this situation, so this is a very good thing to remark. So maybe I should write this on the upper board. So I should write this somehow. There is this space of lambda connections. So if you take pairs L lambda B lambda, L is a line bundle, lambda is in C, and D lambda is a lambda connection. Here I have to put degree 0, because for lambda equals 0, it's no longer this thing. So this has a forgetful map to A1. And so this is actually a nice vibration. So for lambda non-equals 0, the fibers are actually isomorphic to the fibers at lambda equals 1 by some multiplication trick. Or what always happens if you take an algebra and degenerate it to its associated graded, the degeneration family is isomorphic until you reach 0. And so this is this family. It's a nice vibration. So it's a smooth vibration, and all fibers are, there's a connection on it. And so now what happens to this strange isomorphism that wasn't even real analytic here is that first, you know that the cohomology of the fiber over 0 is the same as the cohomology of the total space, is the same as the cohomology of the fiber at 1. But that's the real analytic, the real analytic argument, right? You have a family of smooth varieties, and you know the cohomology is constant also there. Hodge filtration parts, they are all the same, but the Hodge filtration exchange can move in the family. And so this is the isomorphism that's only real analytic, and the complex analytic one is this Riemann-Hilbert correspondence. So it's very nice to see that this comparison of C star square with T star E is not even complex analytic, but it's controlled in two things that come from complex analysis. One is the family thing, and the other one is the real Riemann-Hilbert correspondence. And the family thing is the thing that's only C infinity and not complex analytic. Yeah, thanks for the question. I wanted to say this. And this space is sometimes called M Hodge. Yes, it is. Yes, yes. So there's a way, well, yes. So this actually carries the C star action, and then you can always glue to P1. And there's a twistor family construction, which is only complex analytic, that gives you an interesting thing to glue sort of the same thing again on the tilted copy. And you have to be if you glue, you have to be very careful with what automorphism you actually use to glue. And I think Simpson tells me tells that, yeah, I shouldn't. So I think yeah, yes. Good. I probably shouldn't, but yes, there is this twistor family over P1, but it will not play a role for us. And even worse, at some point, in this lecture series, I will probably extend this to P1 in the algebraic way, which is not the other thing. But there are several natural and interesting ways to extend this vibration to P1. Put it like this. I mean, for the algebraics, there's only one, right? You have a C star equivariant family. So you take just two copies and you glue the family over P1 by taking the inverse. If you're an analyst, that you can take other involutions, like lambda minus one, what's it? Minus lambda one or minus one bar, I guess it's so you have to compose all involutions that you see, and then you get something that looks nice. Yes. Yes. So that's another thing that I will try to explain. There's lots of these little things that come up over and over again, and I will try to come back and say some of them more clearly when I give you some ideas of the proof. But there's a general thing that if you have such a let's come back to this later. There's some general thing about nice families with a C star action, that you can use the C star action to contract the family to the special fibers and thereby compare the cohomology of the whole thing to the cohomology of the special fibers. And then if you're careful, you can also relate this to the cohomology of the fiber at one or at any fiber. And all the three are isomorphic, and these are isomorphisms respecting the Hodge structure. And that's the reason why I know what this Hodge, well, here I know why the Hodge structure is for, because it's a vibration. So this picture generalizes, and I won't even try to give you the most general version, but for this lecture series, I will fix C, smooth projective curve. And yes, I don't like, but at some point I might assume that this genus is bigger than 2, because I mean, most statements, if you formulate them correctly, are true for any genus, but for genus 0, it's just an empty statement. I mean, your moduli spaces are just points, so there's nothing going on. So it's only interesting probably for G bigger or equal to 2, maybe. And you can take you can look at the same problem. You can look at the representations. With value in any reductive group, but I'm for this lecture series, because this is what P equals W conjecture was originally about. I will take GLN, but if you like, you could take G reductive. So what is this? So this is, you take homomorphisms from your GLN and divide by the action conjugation up to conjugation. So this is, if you want to have this explicit, you take 2G. So for each generator of your fundamental group, you take choose generators of your fundamental group. Take 2G matrices, and then you want that the product of the commutators satisfies the relation in your fundamental group. Occasionally, I do intentional spacing. And then divide out by conjugation action of GLN. So this is usually called the Betti cohomology. And you can also look at flat connections. So moduli space of vector bundles with a flat connection. And you have it's called the Dolbeau moduli space, which is the Higgs bundle. So this is pairs E, phi. E is a vector bundle. Rank N on C, and phi is a section but I write it in this funny way, but it's just a morphism from E to E tensor omega. And if you want to know what the reductive analog is, then it's better to write it like this, so you get a section of this. Would even be better to take the dual, but it doesn't matter. And now here you have to add, unfortunately, you have to add some semi-stability. You have to mod out some isomorphism. And again, there's a theorem. So I will not, I mean, at some point I will maybe say something about this, but you have to add an extra condition. That I in some sense I would like to think it's a bit wrong, but I mean the first instance why such a condition might happen here that you saw in this line bundle example is that if we looked at line bundles with flat connections, we automatically knew that the degree of the line bundle was 0. If you take a line bundle together with a section of L goes to L tensor omega, you can do this for any degree, there's no problem. And so sort of this notion of having a holomorphic section of this is kind of too weak to capture all the rigidity of flat connections. So you have to allow this, put some extra thing here. So there's a theorem, and I don't know, there's so many people, famous people involved, that I'm not sure what is the right number of people to put. I don't know. Maybe I try Hitchin, Donaldson, Collette, Simpson. Is this more? Okay. I guess. Well, yes, Hitchin was the first one to come up with a statement like this. Simpson is the sort of the cleanest example that's written, and the others is had made important contributions to this thing. That this picture above extends, so that actually this m-Betty is again homeomorphic to this m-Galois, which is this Higgs semi-stable. I should. And plus the family version using lambda connections. Hold for any G. And even you don't need to take a curve, but then the formulation is even a little bit more complicated. Yes, so I left this. So I put it here. Did I put it? Ah, I forgot. Thank you for reminding me. So now I want to come to this. Plus, there are many variants. So there's variance for other degrees. So it's a good question to come now. So I could replace this degree by degree d here. And then there's a variant that tells you, well, if you want to have something corresponding to degree d, then you should think of a surface with a puncture and fixing monodromy around the puncture. So this is what you could put here, is to put this. And then you take the same quotient and you get this thing for degree d. Would call it m-Betty nd. And then this holds. And degree. How do I fix the RAM? Oh, yes, I have to talk about connections with poles of prescribed structure around the pole. I mean, so I have to allow a singularity of this connection to. I mean, here you have a. Yes. Okay. This is all. Yeah. Okay. This was okay. Yes. Okay. I shouldn't have. Okay. I shouldn't have done this. Okay. Yes. Yes. So I need to think, and I don't know. I don't know. I have to think. So the problem is that, I mean, although this picture is very nice, somehow I believe it should be there, but I'm so yes. So I think it. So in my head it should be there. there is this problem that I was not quite fair about, is that, which is also the reason why all these names appear, especially the analytic ingredients in between, that you might think that the way this is proven is to go through this nice vibration and the Riemann-Hilbert correspondence, and that's not the case right now. So right now, this proof of this homeomorphism is via an analytic procedure that does not go through this family of lambda connections, and the lambda connection picture is something that is proven a posteriori. And it's kind of annoying that it is in the state, but it's nothing that I can do about it right now. So this is not the, so this picture that I gave you is not the way that the proof goes. But I like the picture to have in mind because this, I mean, in general, for d equals 0, these will be singular varieties. And then it's kind of, people like to say that this is a diffeomorphism, but it's, this picture gives you a clearer idea of what this means. You have a C infinity family of singular varieties, and then an analytic isomorphism postponed by this. So this is what you mean by diffeomorphism, although diffeomorphism of singular algebraic variety doesn't quite make sense. Well, yes, stratified diffeomorphism, but it's, yes. Right, that's probably a good way to say. Okay, so the miracle is if, well, I will. Yes, so this is, I think this, because you have this lambda connection family, can make this real analytic. The way this proof goes also has the disadvantage that it really only works for the moduli spaces and not for some, I mean, you might want to think of both sides as algebraic stacks, and then there's no, I mean, it's a very peculiar situation because there's this homeomorphism of the moduli spaces. Also for, on the level of objects, there's a categorical equivalence behind it, but still the geometric thing is missing. And it's kind of even worse that Simpson expands in his article on that the way he constructs this isomorphism doesn't seem to work on this. There's something slightly strange. But okay, so this is, so for n, no, so for n equals d, for n and d coprime, both sides are smooth. And maybe I was planning to say, I mean, maybe you have seen this, but there's a point where I want to come back to this a little bit later, probably tomorrow, where I can remind you why this, how this comes about. And yes. Okay, so this originally came up in an article of Hitchin, and he was interested in this moduli space of Higgs bundles because it forms what he calls a completely integrable system, a very peculiar structure that we have not so many interesting examples explicitly lying around. But then one of the first things I think he used this for was that because this moduli space, we understand moduli of vector bundles rather well in some sense. So know what the cohomology is for a long time and so on. And so there's actually the hope that on this space you can compute the cohomology, and this way compute the cohomology of this Betti moduli space, which is kind of something I want to point out, that this Betti moduli space seems to have the advantage of being given by a quotient of an explicitly given affine variety. It's just matrices satisfying some relation, quotient out by a group action. it's kind of an explicit affine algebraic variety. But as you know, I mean, if I give you equation and ask you to compute the cohomology, good luck. Yeah, I mean, it's not, this doesn't make it easier. But on the other hand, at least for rank 2, Hitchin was immediately able to compute the cohomology of this space. Yes. Yes, so point-wise, there's an equivalent, I mean, so for objects, there's an equivalence of categories. On the moduli space, we have an homeomorphism. But on the level of algebraic stacks, they are not known how to fit them together. So for families of things with automorphisms, it's unclear to match them on both sides. It's just homomorphism, yes. Well, it's real analytic, but it's yes. But it's sort of, if you like stacks, then there's some extra structure on these spaces, and it's unclear how this extra structure fits in families. And as Simpson explains, he gives explicit examples of families where if you just run stupidly through his construction, they don't match. It doesn't say that it's impossible to match these extra structures, but it's not the way it's constructed, it doesn't work. Yes, if you would take this stack of semi-stable objects and take the stack quotient on the right-hand side, then we don't know whether these are homeomorphic as topological stacks. For now. Good. Okay, so now let me, okay, so this was, okay, now I'm running out of time, but I will try to be quick. Just tell the story on the right-hand side. So Hitchin immediately was taken by, that he could compute that the cohomology for rank 2 Higgs bundles, he could compute the cohomology by some trick. And so this actually gives you information on the topology on the right-hand side. So he had a series of students that were trying to do the same thing. So Peter Goten, in his thesis, he computed the cohomology for rank 3 Higgs bundles. And I don't know how it went on then, but Tamas Hausel, who is another student, was also thinking about this problem. And there is, how would you go about? And he did, with Rodriguez Villegas, he did something very remarkable. Can only say it's remarkable. So it's how to go about, how to compute. So, maybe I should put some remarks. The first thing is something I will probably hopefully explain something about, that the cohomology of this. So now I will do, from now on, N and D will be co-prime. And the first thing of this remark is that this cohomology of this Dolbeault moduli space is pure. I will say something why, I hope tomorrow or on Wednesday. And so there's the cohomology. All the cohomology groups seem to come from a smooth projective variety, although it's itself not a smooth projective variety. Although it's not projective. As we saw, this Mbeti space is affine and it's far from smooth. From pure, and the example of GL1 already indicates this. And we will see that there's something more about what the Hodge structure actually is. It turns out to be a Tate only. Okay, so, and hopefully I will explain something in the next lectures on why this is not true. So how to compute cohomology? Cohomology, or favorably with the Hodge structure, but maybe first we only want to compute the cohomology. And there's one famous version. Option. This is use point counting. This is the Weyl conjectures for smooth projective variety. That says if you know the number of points of this thing for knowing this for n large enough or sufficient for many n, determines the dimension of the cohomology groups in a prescribed way, and sort of vectors that look like q to the I correspond to classes in H2I. Now there's a problem that these both spaces are smooth but not projective. Now here we know the cohomology is pure, so in this case, this point counting would actually help, but the point counting here is difficult. So this point counting on Higgs was difficult in the beginning. It has now been done, and twice. So number of these Higgs bundles is difficult. But there's now two papers that do this. One is by Schiffmann, and the second paper by Hongjie Yu. I hope I got this right. No. And I forgot the dates. They both appeared in the annals. And they're quite recent, and they weren't available at the time when Tamás was thinking about this. But so Tamás did something with Rodriguez Villegas. He did something crazy. But so this variety on the right-hand side, I can essentially define over the integers, maybe after joining a root of unity. And I can do this pointer counting as possible using representation theory. And the output is get polynomials in Q. So for example, for this D star to the 2G that I would start it out with, it would give me Q minus 1 to the 2G. And you see that this looks like, if you multiply it out, it looks really what I would expect from this exterior algebra, except that these Qs all appear in the wrong dimension. And so from this thing, they came up with a conjectural formula for the cohomology of this, both M-Betty and the cohomology of the Higgs moduli space with its Hodge weights. And what's amazing about this formula, I have to stop, I guess. Yes. So I don't write anything more. What's amazing about this formula is two things. First, in order to do this, you have to guess for these powers of Q in which cohomological degree do they lie. That's amazing. The second thing that's amazing about this formula is that, well, if you don't know that your cohomology is pure, there might be lots of cancellations. So if you do this point counting, it's because how does this counting go, it's because some endomorphism on the cohomology you compute its trace, alternating trace on the different degrees. But now you have these powers of Q that can appear in degree 3 and 4, and then they will cancel. What's amazing about their formula is they guess this, and they guess that there's lots of cancellations. Yeah. Okay, so they come up with this conjecture. And what's the, I mean, how do they come about? These formulas, they are given in some generating series. You can put them in some nice generating series that is given by rational functions. And so the first indication why it might be reasonable to make such educated guesses is that usually if you write down nice formulas and you try to put them in your computer and you do one typo, the result of these things, of these generating series you get is not a polynomial, but a rational function. So it cannot be, you made a mistake. So it's this guesswork, if you want to do it in this generating series way, it requires an art to get something out that gives you a polynomial. And also you had the known result for degree 2, rank 2 and 3 available. So you can check with these. The story behind this is that actually they checked with rank 2 and the rank 3 didn't match. And then they checked the article and found the mistake, the typo in the formula of the published article, which is kind of amazing. Which was already an indication. Okay, good. So that's the story about this thing. By now, this is proven. So they did the point counting, and then Anton Mellet proved that this formula they get actually coincides with this conjecture formula, which is kind of amazing. But they also, and that's the last thing I want to say, they found some structure on this Betti space that is a bit like what we've seen for this hard-Lefschetz property in Geordie's talk yesterday. They found some symmetry that looks like a hard-Lefschetz symmetry, but which goes between the wrong cohomological degrees. So it's a slightly tilted hard-Lefschetz. And this led to this P equals W conjecture, because I guess it was Luca Migliorini and Marc de Cataldo hearing talks about this tilted version of a hard-Lefschetz property. They knew from their work that they know one more example in the world where such a shifted hard-Lefschetz property appears, and that's an intersection cohomology. And so they said, so they, with Tamas together, they set about and tried to see whether there's some geometric filtration you can find on this right-hand space that produces a filtration. There is some known filtration here that also has this shifted Lefschetz property. Because these are so rare, let's see whether these two agree. They computed for rank 2, both sides showed these agreed, and the P equals W conjecture was that actually the geometrically defined filtration here, coming from intersection cohomology, coincides with the weight filtration on the right-hand side. So that's why it's called P equals W. W stands for the weight, and P for the perverse filtration here. Okay, I will come to more details in the next talk. Thank you.
Thanks for the lecture. So, are there any questions?
Yeah, I wanted to ask, so this purity of the Dolbeault moduli space, even though it's not projective, can you prove this from the fact that you know that it's projective over an affine space?
Yes, so it's yes, this is how this will go. So I haven't talked about the Higgs infiltration, but indeed, so this Dolbeault moduli space has a proper morphism to an affine space, and this is a proper morphism that is equivariant to a C star action. And in this case, you know, again, from a similar thing that we started out with, that the cohomology of the total space is isomorphic to the cohomology of the zero fiber. Now, the cohomology of the total space is not pure, but it's not pure because it's smooth and not projective, which means that the weights could in principally be too high in the cohomology groups. The singular fiber, the zero fiber, is projective but not smooth. So its cohomology is not pure because it's singular. So there could be weights that are too small. but they are isomorphic, so none of the two things can happen. That's essentially the argument.
Thanks.
Are there any other questions? Okay, then begin. Thanks again, Heinloth, Jochen. Okay, so the next speaker is Geordie Williamson, and he's going to talk about Hodge theory just beyond geometry, second act.
Thank you, Luigi. Today, I am talking about polytopes. So today there will be no Hodge theory. One thing is that two people, one person in person, one person online, said that some of my writing was too small. Please yell at me if my writing becomes too small, or even just speak in a normal voice and say, your writing is too small. Yeah, so just to remind you where we are, I'm talking about these situations in mathematical nature where Hodge theoretic structures show up, where there's no obvious variety. Yesterday, I talked about the co-invariant ring, and this was part of this kind of big story that involving circle bimodules and casualistic polynomials that I didn't talk about, basically because the combinatorial load is rather heavy. And today, I want to talk about polytopes, and then I will explain how Hodge theory solves a very fundamental question in the theory of polytopes. And I think it's a very beautiful story. I also think that this particular polytope story is the kind of easiest point of access into combinatorial Hodge theory. So if you actually want to, so I don't think that I'll get to the proofs of the, for example, hard Lefschetz for simple polytopes. However, if you were to read this proof, you can, it's about 10 pages or something, and it's very beautiful interaction of hard Lefschetz and Hodge-Riemann relations, and it's understandable in a small amount of time, whereas all of the other applications really require a lot of baggage from the particular subject. Like, you know, in matroids, there's really a lot of baggage coming from matroids. In circle bimodule theory, there's a lot of baggage coming from Coxeter groups and their combinatorics. So that's why I'm doing this example in more detail, because it's the most accessible. Okay, so a D polytope. So we start off with V1, V2, a large number of points inside R to the D, and not contained in any hyperplane. In any affine hyperplane. And a D polytope, so a D-dimensional polytope is a P, which is the convex hull of V1 up to Vn, or equivalently, it's the set of all lambda I Bi, where the lambda I are bigger or equal to 0, and the lambda I sum to 1. And usually, so the fact that they're not contained in any affine hyperplane ensures that the polytope is kind of, it has an open interior inside R to the D. And usually we assume that 0 is in the interior of P, in which case we can define the dual polytope to be the set of all functionals which take the value at most 1 on P. And I'll go in a little bit later about vertices, edges, etc. But yeah, so that's the dual polytope. Sorry, RD star. So let's just call this V once and for all. So this is V star. And examples. So in dimension 1, there's basically one polytope. In dimension 2, I get something that looks like this. Okay, and it's a pretty straightforward thought exercise to see that any 2 polytope basically looks like this. And in dimension 3, there's many, many, but an example might be the cube. Or the octahedron. And these are dual. Okay, so in the each of the faces of the octahedron correspond to the vertices of the cube, etc. And a basic fact in the theory, which is kind of like the first theorem in polytope theory, is that any polytope may be described as an intersection of affine half spaces. And in the polytope literature, a description like this is called a V description. And so in this particular example, you know, I describe it as the intersection of this affine half space, this affine half space, this affine half space, etc. And such a description is called an H description. Okay, so any polytope can be described in one of 2 ways. And a remark, so there's 2 very important basic concepts. So a polytope is simplicial if it's generic in the V description. So what I mean by that is that, so I'm doing this somewhat out of order. So I'll explain in a second what the combinatorial type of a polytope is. But basically, this is all of the vertices, edges, faces, etc., and their incident structure. And notice in this example, if I wiggle this vertex a little bit, it keeps the same combinatorial type. So that would be simplicial. But if I wiggled this vertex a little bit in the cube, I would break that face into 2 triangles. And so this is not simplicial. So this is simplicial. If I wiggle a vertex a little bit, I don't change the fact that it's combinatorially an octahedron. So that's what simplicial means. And simple is the dual notion. Means generic in H description. Okay. And you can convince yourself that it's extremely rare for a polytope to be both simple and simplicial. And you might like to ask yourself which polytopes are both. Yep. I said it does. Can you see that? They're very important, so let's spend some time. Does it? No, I mean that if you think about it, you'll decide that there's only a very small class of polytopes that are simple and simplicial, and you'll be able to tell me which ones they are this afternoon. Yeah. Okay. If you think about this for a little bit of time, there's a nice answer. Okay. Yep. Yes. These are dual notions. Okay, yeah. So apologies, I'm doing this slightly, I would use an Australian expression that is not polite, so I won't say it. In a second, I will define the combinatorial type. The combinatorial type is what faces are there, what edges are there, etc., and how do they sit one amongst another. Yeah? And simplicial means if I wiggle the vertices, I don't change the combinatorial type. And simple means if I wiggle the hyperplanes, I don't change the combinatorial type. So yeah, here, if I move the vertex a little bit, it still has five vertices, it still has 5 edges, and they still have the same intercept structure. So this is a simplicial polytope. This one's not, but it's simple. Yeah. So try to find another exercise. Try to find a polytope that's not simplicial or simple. Yep. Is that a hand or is it scratching the head? Absolutely, yeah. So I mean, I can write down, like in that example, if I take 70 points on a line and take their convex hull, 68 of them play no role in the polytope. And we often call such points dormant. So I don't need to assume that these vertices are the vertices of the convex hull.
Okay, so if you do that, then you move one of the dormant points around, that seems that it'll break.
Yeah, that's just stupid. So
I see.
Yeah, so if you want, you can assume there's no dormant vertices.
Okay. And I mean, with the cube example, I still don't really understand. I mean, it seems like if you move one of the vertices around, it's going to keep it's going to keep everything.
So here's 4 points that lie in a plane in R3. Okay, it doesn't really look like it, but please use your imaginative capacity to improve this picture, yeah? So when I move this vertex up, yep, the following happens.
Oh.
Yeah, this point is no longer in the same plane as these 3.
Yes. Okay.
And I break the fact that I have a square. Yeah, another way of saying being a simplicial polytope is all of the maximal dimensional faces, the facets, are simplices. Yep, so in 3 dimensions, that means every maximal dimensional facet is a triangle.
Ah, okay.
So yeah, so another remark is that and this is kind of important if you're thinking about this world, that the V and H descriptions can have radically different complexity. I'm not making this remark for any reason like to do with this course. It's just interesting. So if you take a cube in R to the D, so the vertices can be taken to be all the plus or minus 1 vectors. So it has 2 to the D vertices. So this is the V description. But if you want to describe it by equations, you just say that one of the coordinates is either less than 1 or bigger than -1. So you get 2D equations. Okay. So, you know, for a computer scientist, this is a big difference. Yeah. So a cube in, you know, a dimension 100 needs 2 to the 100 pieces of information in the V description, whereas in the H description, it only needs 200. Okay. And linear programming is the passage between, I mean, the linear programming is many things, but you can see it as the passage between the V and the H descriptions. Okay. So, you know, one of my kind of weird interests in the mathematical world is in kind of some kind of linear programming. So maybe just to motivate, because when someone explained to me linear programming when I was in 2nd or 3rd year, they explained to me, you have this kind of, so basically, like, if you haven't seen what linear programming is, what you want to do is you have some polytope like this and you want to maximize a function. And what you do is you intersect, you find some point in this polytope, which is very easy because intersecting spaces is a very easy thing to do. So we can find some point, and then you basically go along an edge if you increase this function, and then you journey up to here, and then there's no edges on which you can increase your function, and so you've solved your linear program. And you have probably used linear programming about 20 times today on your phone without realizing it. Yeah, so it's an incredibly fundamental algorithm in computer science. And I remember when someone first explained this to me, I thought, of course that's what you do. Like, you know, it's the most obvious algorithm in the world. Like, why do we worry about this so much? And the reason is because it is incredibly effective. So recently I had some fascination with some kind of polytope in, I don't know, it was like in 3 million dimensions and had 50,000 equations or something. And I type it into one of these solvers and it gives me the answer in like under a second. And it's just totally amazing how fast this is. And we have no understanding of why it's so fast, basically. I mean, that's a vast simplification, but there's basic questions about linear programming that we don't understand, basically because of this. You can write down some innocent thing, but you might need to do an enormous number of steps in the algorithm. And in fact, there's this famous Klee-Minty cube where linear programming, if you do a stupid thing, takes exponential time. Yeah. But anyway, I'm kind of getting sidetracked. But polytopes are very interesting. Yeah. Sorry. Yes. Absolutely. Yeah. So they're dual. Yeah. So the V description of the octahedron is very effective. Yeah. Yeah. So the octahedron would be just opposite. Okay. Another reason that I find this polytopal world fascinating is if you think about linear algebra, we know very well how to do operations in linear algebra. If I say, like, here's 2 points, find the line between them, we can do that very well. If I say, here's 2 hyperplanes, intersect them, we can do that very well. Now, if we add polynomials into the equation, we get algebraic geometry. Yeah? And we spend our lives studying algebraic geometry. Yeah? The other thing that we can do is just take linear algebra and replace that innocent equals with less than or equal to 0. Okay? When we do that, we get the world of polytopes. And in some sense, you know, and my gut feeling is that we have no idea of how complicated the world of polytopes is in high dimension. And I feel like this is one of these situations where we cannot even glimpse it because of our kind of human limitations. And so anything that allows us to see the world of polytopes, even get a glimpse of what happens in high dimension, is incredibly valuable. And that's what this extraordinary McMullen's conjecture does. And that's what I'll explain towards the end of today. So we get a glimpse of what simplicial polytopes look like in large dimension, which is really amazing. And also, you know, the other beautiful parallel between kind of the algebraic geometry world and convex geometry is the theory of toric varieties. And so in some sense, algebraic geometry casts this convex geometric shadow. Okay? And so toric varieties are another way of getting some picture of the vastness of algebraic geometry. Okay, so we have the notion of a support function. So this is an affine linear function, which is bigger than or equal to 0 on our polytope. And a face is the set of f of v equals 0 for v in P, where f is a support function. Okay, so here in this example before, what are the possible kind of support functions? So I could start off here. So here's my affine linear function that's positive on the whole polytope, and the intersection with the polytope is nothing. So nothing is a face, the empty set. And then my support function might look like that, in which case I get a vertex, or my support function might look like this, in which case I get a face. I get a one-dimensional face. Okay. And my support function might be 0, in which case I get the whole polytope. And the dimension, so if f is a face, its dimension is the dimension of its affine span. Okay, so this face would be dimension 0, this face would be dimension 1, etc. And then to a polytope, we associate the partially ordered set of faces ordered by inclusion. Okay, and this is called the lattice of faces. And so, for example, if this is our polytope, then we have the empty set, and then we get a picture like this. Where these are the vertices. So if this is vertex labeled A, and this is vertex labeled B, and this is labeled A and B, and then this face is AB. And then we get everything up the top. And this is called the combinatorial type. Okay. So to every poset, to every polytope, we associate this poset, this lattice, and the lattice is the combinatorial type of a poset. And many things in polytope world are basically like my evolution with polytopes is I come up with some kind of natural sounding statement. I then convince myself that it's true. I try to write down a proof, I struggle. And then I find some paper that explains to me that it's wildly false. Yeah. And at some point you just get used to this happening so often that you start not believing anything that you think should be true. So remark. So this is the beginning of the kind of complexity. So what we can do is fix a combinatorial type. So this means I want 70 vertices. I want the following faces. I want the following edges. I want the following faces. And I can give that to you, and you can try to find an arrangement of points that satisfies that. So this is called the realization space. Of a fixed combinatorial type. Are basically can be made to be basically the same, and I won't say what basically the same means, with any semi-algebraic set. So an example of this is so there exists a combinatorial type realizable over Q adjoined the golden ratio, but not over Q. Or given any number field, there exists a combinatorial type realizable over that number field, any real number field, but not over any subfield. Okay. Like I find that shocking when I first learned that. I find that shocking. Yep. Exactly. Exactly. Yeah. So realizable over a particular field, over a real field, means that I can find vertices with those coordinates, or equivalently hyperplanes, the H description with those coordinates. Yeah. So I won't explain why this is true. So this is something that, this is an example. So if I look at basic combinatorial types, like I look at the combinatorial type of a triangle or something like this, it seems very flexibly realizable. Like, you know, it seems easy. And so you get a sense from small examples that realizing polytopes is kind of a free process. But what happens in large and complicated examples is that you get more and more kind of constraints propagating, and you can arrange these constraints to give you any equation over the rationals, or over the integers. Okay. That is a good question. I don't know. I don't know. I suspect that for 4 polytopes. So in this world, as I'll try to explain in a second, 3 polytopes and below are very easy. And all the complexity starts in 4 polytopes. And I suspect that this already happens for 4 polytopes, but I'm not sure. No. Yeah. Okay. And I would love to explain, like this is one of my favorite things to explain, but there's no time. So, yeah. This means yeah, so for example, so what this means is stronger than what I'm about to say, but an example of what this means is given I can find for any semi-algebraic set, I can find a combinatorial type whose realization space has the homotopy type of that semi-algebraic set. Okay. And something slightly stronger is true, but I will probably mess it up if I try to say it. Okay. So face numbers. So we fix a polytope P, a D polytope. And the most basic invariant you can associate to this are the face numbers. So Fi is the number of I-dimensional faces. And this gives the F vector, which is F0, F1, Fd. So for example, an n-gon has F vector. So there's n vertices, n faces, so n edges. One. Okay, and the tetrahedron would be 4, 6, 4, 1. Is that right? 4, 6, 4, 1. Oh, and also I kind of, yeah, so we've also got the so I said that the empty set is a face and this is a dimension -1. So this is F-1. And then a basic question is what F vectors can occur? We should be able to answer this question if we have any hope of understanding polytopes in a given dimension. So for d equals 2, I already gave the answer. So any polytope is like this. That's a nice simple exercise. And so d equals 2 is fine. D equals 3 is actually a theorem. And it follows from something called Steinitz's theorem. So this says the following beautiful thing, which is that if I have a 3 polytope, I can project it onto the sphere. And so I get a triangulation of the sphere. And I get a triangulation of the sphere, which is called polytopal. So it can be realized by a polytope. And what Steinitz's theorem says is that in dimension 3, any triangulation of the 2 sphere is polytopal. So if I give you a wacky, crazily drawn triangulation of the 3 sphere, I can straighten it all out and find a polytope with that. Okay. And now it's a simple exercise to write down what the F vector is. And that statement of Steinitz's theorem is it's a bit of work to prove. Yeah, I think it was proved, I'm not sure, probably like 1880 or something. And d equals 4, it's unknown. Okay, we do not know, Jochen? No, I mean, sorry, I just misspoke. I mean cell decomposition. Yeah. Yeah, I'm not assuming simplicial. Okay. So d equals 4 is unknown. We still don't know the answer to that. How innocent is it? You know, you have 70 points in R4, take their convex hull. We do not understand what can happen when we do that operation. Totally amazing. Yeah. Well, people argue about what the dimension of the empty set is, but for me, it's -1. Okay, so there's one -1 dimensional face, and it is the empty set. And so that's why I've got this 1 here. And this is F1, this is F0, this is F1, and this is F2. Okay. I'm about to chuck it away. And I'm about to chuck away FD2. So yeah. How to like set up this theory is important, and I'm going to do the proper way in a second, but just I'm choosing the most intuitive way to get started. Yeah. No. It's not one of these situations where dimension 4 is special. It's a situation, I think, in which every subsequent dimension is more complicated than the previous one. So we definitely know that all triangulations are not polytopic, and all cell decompositions are not polytopic. And there's a vast difference between the two. Like the vast majority of triangulations of the 3-sphere do not come from polytopes in a way that somebody can make precise, but I cannot. So that's the first thing that we don't. So we know that is a fact. And now you can ask, what are the F vectors of polytopes or triangulations? And we know the answer to neither. Yeah, total coincidence. If you did the cube or something, you would get something not symmetric. Yeah. Okay, so, and McMullen's conjecture is a complete answer for simplicial polytopes. And what it says is that there exists P with F vector blah F, if and only if. So this takes a little bit of work to explain, which is the rest of the lecture. But basically, there's something called Dean-Somerville. So these are the equalities that must hold. And then there's inequalities, which are called M vector. And M is for Macaulay. And this is to be explained. Okay. But I don't know. Like, this is one of the, I think many combinatorialists would regard this as one of the kind of major theorems of the last 50 years. It's an absolutely extraordinary theorem, and its proof is via Hodge theory, which is very nice. And it also just gives us some picture of what this incredible landscape of polytopes in high dimension looks like. Yeah, so it's a theorem. It's a theorem due to Stanley and Biller-Lee, and I'll explain one direction in this course. That's correct. It's Peter McMullen. And I don't know, it's, you know, there's just these absolutely remarkable stories in mathematics. And I think Jochen was highlighting one in, you know, Tamash and Rodrigo staring at some counts that give you like very poor information about something and guessing what the answer is correctly. Like, that's totally amazing. This is another example of such a thing. McMullen had very little to go on and wrote down these inequalities, which are for me totally incomprehensible. And then people slowly realized what the inequalities meant and connected it to this work of Macaulay, and the conjecture turned out to be right. And it's just totally remarkable that he managed to make this conjecture. Well, if you know the F vectors of simplicial polytopes, you also know the F vectors of simplicial polytopes via duality. Yeah, and then there's the whole world of things that are neither simple nor simplicial, and there we have no idea. So now I want to do what I promised, which is to fix up the counting procedure. So we change count slightly. And for those that know toric geometry, this change will appear very natural. So I wanted to find a polynomial which has equivalent information to the f vector, but counts it in a slightly better way. So we start with our polytope. So for example, and we associate to this the fan spanned by P. And so what that means is that I'm always assuming that 0 is inside my polytope. And so then I look at this. So here's my polytope. And now every face I let generate a cone going out from 0. And this is called the fan spanned by P. And then we count in the following way. We find FP to be the sum over the cones. So a cone is basically, so the cones are, I have this 0-dimensional cone, and then every other face of my polytope. So for example, a vertex of my polytope spans a 1-dimensional cone. An edge of my polytope spans a 2-dimensional cone, etc. And now I count these with the coefficient of t to the d minus the dimension of my cone. Okay, so here I would get, so here d is 2. And so I get t squared corresponding to this point. And then I get plus 4t plus 4. Is that what I wanted? Yeah. Okay. So these correspond to the 4 rays. And then these correspond to the so these correspond to the 2-dimensional cones. Okay. And you can see that essentially by ignoring this term, I get the f vector, but now I've just flipped it. And then we write, and this is the step that's very natural from toric geometry, we write fp. So this is a polynomial in T, and we evaluate at q minus 1. And this is the sum over hi q to the I. And so this thing is called the H vector. Okay. So in this example, we would work out q minus 1 squared plus 4q minus 1 plus 4, and we would hopefully get q squared plus 2q plus 1. Okay. So what does this H vector count? Yeah. So, sorry. So I have a polynomial. So FP is a polynomial in T. And I just evaluate T to be Q minus 1 and collect the coefficients of the powers of Q. Well, at the moment, Q is just another variable. It's just a renormalize. So, you know, if I wanted to, I could write down some formula involving binomial coefficients that from the FIs produces the HIs. Yeah. Yeah, it's basically the F vector, except I've forgotten one term or something like that. Yeah, but it's just the F vector kind of written the other way, like written from, like I start at F0 and then go back down to FD at the bottom. At the moment, well, it will be simplicial very soon, but at the moment, this makes sense for any polytope. But I don't think that we know the meaning of the HIs if it's not simplicial. Yeah. So the HIs are basically meaningless outside of the simplicial case, is my impression. So the HI have a meaning. So if P is simplicial, we can ask, what do the HI count? And the answer is actually really beautiful. So this is called the rocket ship journey. So here's our polytope. And what we do is we imagine that we live on a polytopal Earth. So this is a very wonky picture of Earth. And we launch a rocket. Okay, let's say that we launch from here and we go this direction. Okay. And now we ask ourselves, we list the facets. So facets are faces of dimension d-1 in the order they become visible. From rocket. Okay. So here, this one, as I'm journeying up in my rocket, and then first this one becomes visible. And then as I go out, this one becomes visible. And then I keep going out and nothing more becomes visible. But then I have to take my rocket ship to infinity and beyond and come back this way. And now I list the facets in the order that they disappear on my journey. So out here, all of these three facets are visible. So this would be 1, 2. And now as I cross this line here, this facet becomes invisible. So 3. And then as I'm coming in here, this facet becomes invisible. 4 and 5. Okay, so I list my facets as F0, F1, Fn-1, Fn. This is the order in which facets appear. And this is the order in which they disappear. So I'm about to get yelled at for writing too small, but I hope you. Okay. I don't think I understand. Yes. I never thought of that. I don't know. That's awesome if it's true. I need to think if it's. This is a very good exercise for us. I never thought of that. Okay, so this ordering matters, it really matters enormously where you launch your rocket ship, of course. Yeah, but no matter how you launch it, you get a very remarkable structure on your polytope called a shelling. But this is called a shelling order. So another way of kind of, I was mystified by this terminology until at some point I was like peeling an egg. And you take off a piece of the egg and then you take another piece of the egg, etc. And if you take these faces away in either order, then you'll see that this way of removing the faces of the polytope is very nice. And you can say what very nice means, and it means a shelling. And that's what combinatorialists call a shelling. Yeah? But anyway, I won't go into detail about what very nice means. And now there's a really beautiful little thought exercise. So if you think about, the thought exercise is the following. So if you think about so now you basically use this order and look what you're doing to the F vector. So when you take this first one, what you're doing, so I should have labeled this 0, 1, 2, but anyway. So here you add 1 plus 2q plus q squared. Sorry, 1 plus 2t plus t squared. And so F0 contributes 1 plus t to the d in general. So these are the faces of a simplicial cone. And Fn contributes, by the time we get to the final one, we've counted everything except for this open cone, this open piece, which is counted by 1. And the thought exercise is that Fi contributes 1 plus t to the d of Fi, where d of Fi is the number of facets in Fi minus the union of all the earlier ones. Okay. So we no longer have to solve this exercise. Very good. And so what this H vector is, so now when we substitute q plus 1, we get 1 plus t plus q, 1 plus q minus 1. So we just get q to this coefficient. So what this is doing, so this says that the hi, so a consequence of all of this, is that the hi is the number of fi such that d of fi, fj, such that d of fj is j. Okay, so the coefficients of these h, thank you. So what we're doing in this H polynomial is counting the facets with a particular coefficient coming from the Schelling order. Yep. Yeah, sorry, the number of facets means dimension d minus 2 faces. Okay, so here, for example, I have 2. So this corresponds to a q to the q squared. These all correspond to a q, and this one gives me, oh, sorry. These all correspond to a q, and then this last one gives me a 1. So, So for a simplicial polytope, yes, and I've just explained why. In general, no. And in general, the HIs are meaningless as far as I can make out. So now there's a beautiful, here's a beautiful thought exercise. I claim that HI is HD minus I. Why is that? Reverse rocket ship journey, yeah? Okay. So that's really beautiful. I think that this quantity is just flipped for the reverse rocket ship journey. And so we immediately see something like Poincare duality. Okay, so HI this is called the Dehn-Somerville relations. Okay, and these are really horrible if you write them in terms of the FIs. And that's what Max Dehn did in 1905 for 4 and 5 polytopes. So he discovered these relations in dimension 4 or 5, and they're rather complicated binomial coefficients things. And then Somerville generalized it to polytopes. And an exercise is that H0 equals HD is equivalent to what formula? So this is equivalent to something that you know and love. And the question is what? Yeah, so I went way slower than I thought. So I guess yeah, so I can just do this next time. So I'll stop here.
Okay, are there any questions for Geordie?
Okay. So maybe this was just a bit too fast for me, but I didn't quite get the thing with the reverse rocket ship. Because I mean, clearly you cannot choose the same starting point and just launch the rocket like inside the polytope.
Yeah, you're allowed to. Like here, like this rocket ship journey is just a journey through the polytope.
But then I mean, can't I see like all the faces?
Like, let's imagine here we go on the reverse one. So then we see 5, and then we see 4, and then we send 3, and then from the other side, we come right in, and then this one's obscured, and then lastly, this one is obscured.
I see. So you're only allowed to look forward.
No, I'm allowed to, I have a spherical rocket ship in which I'm allowed to look in all directions. Oh yeah, you're not allowed to look. So maybe it's better to think about, this is actually the way that I think about it, is I imagine like a polytope in a completely black room, and I have a light source.
Okay. Okay.
Yeah. So I'm illuminating one facet, and then as I move my light source out, I illuminate more and more and more and more.
Okay, thank you. Now I see it.
I have a question. So right here. So is this theorem that the HIs equal the number of FJ such that whatever, is that true for I guess, a generic rocket ship journey? or something?
Yeah. Oh, sorry. So I should, yeah. So there's a requirement on the journey, which is that it's not parallel to any face.
Right. So like an open set.
Yeah. And
Okay.
so probably there's more requirements than that. But anyway, for a generic rocket ship journey, this is correct.
Okay. Thanks.
Yeah.
More questions? Okay, if not,
So are the Dane-Somerville relations, are they just false in the non-simplicial case?
I don't know. Does anyone know? I don't know. Good question. What happens with Dane-Somerville in non-simplicial case?
They're replaced by Dane-Somerville equation for the generalized H vector. So it's quite unlikely that they also hold for the H vector.
Yeah. So what? Yeah. Yeah. That would. Yeah. My suspicion is also they would just fail, but I don't know if there's any kind of replacement. Yeah. So what Luke is alluding to is the fact that for a general polytope, there's a generalized H vector, which has less meaning in polytope world and a very beautiful meaning in toric variety land. And everything that I'm kind of saying today is fine for the generalized H vector, but the issue is that that doesn't actually tell you much about polytopes anymore. I mean, it tells you some things, but it's like polytope people kind of laugh at me when I, say how wonderful the generalized H vector is. So thanks.
okay, other questions? All right. So I guess we can thank Geordie again. Thanks. All right, so welcome back for the afternoon session. So it's my pleasure to introduce Bruno Klingler, who will talk about, don't remember, the program?
Hodge Theory between algebraicity and transcendence.
Right, thank you so much.
All right, so first of all, let me summarize what we did yesterday. So yesterday we started with X, C, and algebraic variety. And for all the talk, I will assume it is smooth and projective. So I repeat it. And then we saw that we can linearize this into a Hodge structure. The way we do it is that we consider the Betti homology of the associated analytic space in the usual topological space. So it's locally compact, so you can just take it's a singular homology with coefficient in Z. And on this V module, once you tensorize it by C, you construct a Hodge filtration, which is in some sense an algebraic shadow of, just a shadow of the algebraic structure on X. So, and you, for doing this, you go through, for instance, de Rham homology, algebraic de Rham homology. So, and then we saw that actually, so you get a complex filtered vector space, and we saw that actually it's much more, it's a polarizable Hodge structure. So I described precisely the meaning of those words yesterday. And finally, out of this, we get a group, which is the Mumford group of X, or more generally of any Hodge structure. And this group is an algebraic group of a Q. And because the category of polarizable Hodge structure is semi-simple, this group is actually reductive. All right, so this is what we did. And then I moved to the variational setting. So in this situation, we had a family over a base S. So S, everything is over C again. S is quasi-projective, and this morphism is smooth and proper. And then on each fiber is a smooth projective variety. So I get this gadget and I put those gadgets all together on the base S. And out of this, I get the notion of the variation of Hodge structure, which is more of a polarizable. And I described how from this, actually, you can pass through maybe a much more convenient, depending on your taste, description, which is the notion of period map, which is a map from the complex analytic space Sn to a quotient of a period domain that I call the Hodge variety. And actually, this is a variety, but in the complex analytic sense. So usually this guy has only a complex analytic structure. It's not an algebraic variety. And this map is holomorphic. Let's say C analytic. And here, there was a crucial ingredient in the definition, which was Griffith's transversality. And this Griffith's transversality here is given by the fact that the differential maps the tangent space to Sn to actually a holomorphic distribution on D mod gamma. Namely, it is in what is called the horizontal tangent bundle of D mod gamma. And I also explained that this horizontal tangent bundle actually comes from the Hodge theory. Namely, it is associated to the -1,1 part of the Lie algebra. So usually this inclusion is strict. And then the main invariant out of this was the notion of level. So the level of a Hodge structure is actually the depth of the Hodge filtration on the Lie algebra of the associated Mumford group. So, and so we get the level, and once we have this level, actually we can define the level of the variation, which is the level of the generic Hodge structure in the variation. Okay, and I finished the lectures by defining the Hodge locus. So I remind you the definition. The Hodge locus was just a collection of points. So it is a subset of Sn. So this is a set of points in Sn such that the Mumford group at the point S is strictly contained in the generic Mumford group. In other words, there are some exceptional tensors, Hodge tensors, appearing in the tensor powers of the Hodge structure at that point. And explains that the description of this Hodge locus is kind of nice in terms of this period map, because so you have this period map. And inside these Hodge varieties, you have countably many copies of Hodge subvarieties, which are guys of the form D prime mod gamma prime for subgroups G prime of G and subspaces D prime of D. And this union is countable because the groups are defined over Q. So this is a countable union. And then the Hodge locus is just the fiber product. Namely, you get the set of points here, which with image under the period map phi lies in this union. So you see that already in the description, you see something that was not clear at the local definition of the Hodge locus in terms of Hodge classes, is that this is a countable union of analytic subvarieties because you take the plane image of those guys which are analytic. All right, so, and I started, let me recall fast the first example that I gave, which was the universal elliptic curve. So S in that case was just the moduli space, the coarse moduli space of elliptic curves. And I take the universal elliptic curves over that. I look at V being R1 F lower star. So this is a variation of Hodge structures of weight 1 and actually of level 1. And then I explain that in that case, the period map is an ISO. So, and the inverse being given by the J function to the upper half space modulo SL2Z, basically. So in that case, the Hodge locus of S with respect to that variation, well, it was entirely described. You didn't have to look at very fancy Hodge classes in some very high tensor power of this H1 of the fibers, but only in the endomorphism. And so actually this was the union of the guys of the form J of tau, or the class of tau if you want, for tau in H imaginary quadratic. And then a basic result of transcendence tells you that actually these values of J of tau, they are in Q bar inside C, which is actually Sn. Okay, so this was this first example. So what I want to do now is to give some more examples so that you get, of course, this example is purely arithmetic because everything happens on the base of dimension 1. So it's a special locus. I mean, this Hodge locus is a countable union of points. Okay, so this summarizes what we did. So now let's move on. So of course, the most obvious next example is the generalization of that one. Namely, you take the universal family of abelian varieties. So AG is a moduli space of principally polarized abelian varieties, and this is the universal abelian variety of it. And again, you take V as being R1 F lower star Z. So this is a family of weight 1 Hodge structures. So this is again level 1. Now, what is a period map? Well, actually, the period map again is the identity. You are identifying AG with the quotient of Ziegler half space by GSP2G. And what is the Hodge locus? Well, I will not describe the entire Hodge locus. To do that, you would have to really understand in terms of group theory the identification of AG. I don't want to do that, but I just want to indicate a few guys that lie in this Hodge locus. So similar to the case of elliptic curves, you have some points, isolated points, which are of purely arithmetic meaning. Namely, you have the points corresponding to a abelian variety with complex multiplication. Okay. And if you want some positive dimensional components, well, you can look at the locus where your abelian variety splits or is isogenous to a product, a non-trivial product. So you can put there AGK, which is the set of points in AG, such that the corresponding abelian variety AS is of the form AK, an abelian variety of dimension K cross an abelian variety of dimension G minus K, or K between 1 and G minus 1, okay? And again, what you can prove in that case is that this Hodge locus is a countable union of algebraic subvarieties of AG defined over Q bar, and they are dense for the usual topology in AG, okay? Even that locus is already dense. All right, so now let's move to a more interesting case, because you see that in those two cases, actually, it was kind of exceptional, namely the Hodge variety D mod gamma was actually algebraic. Here it was AG. But in those cases, the level was 1. So there was no Griffith transversality to be taken into account. So let's move to a case where this does not happen. So what you do is you look at the universal hypersurface, smooth hypersurface of degree D in Pn plus 1. So family of smooth hypersurfaces of degree D in Pn plus 1. So this means that if I look at the space of all hypersurfaces of degree D, and this is the projectivization of H0 of Pn plus 1 with coefficient in O of D, okay? And I remove the discriminant locus where those hypersurfaces are not smooth. So as a complement of this discriminant locus is this very big Zariski open set in this projective space. And so over each point here, I have a hypersurface of degree D, and I consider this family that I denote by X and D. So this is a universal family of such. So for hypersurfaces in Pn plus 1, so now we have varieties of dimension n. What is interesting is the cohomogene middle degree. So what we do is we take for V R n F lower star of Z. So I get a variation of structures of weight n on U and D. And now we can ask, can we describe the Hodge locus there? So this is a very classical topic for surfaces in P3. So started by the Italian School of Algebraic Geometry, actually. So suppose that n is equal to 2. So now I'm in P3, and I looked at surfaces in P3. Right? Then there is a classical result of Noether that tells you that if the degree of that surface is at least 3, then the general surface in this family, the general surface XS in U2D has pk number 1. So the pk is just Z. Okay. Which means that any curve in such a surface is basically a complete intersection of the surface with a hyperplane in P3. So what is the Hodge locus? Well, we don't know, but what we know is that it contains what is called the Noether-Lefschetz locus. So it contains the Noether-Lefschetz locus of, let's call it F. So F was this morphism. So, and what is this Noether-Lefschetz locus? This is a set of points in U2D such that the pk is not Z. So such that rho, the pk number of that surface is at least 2. Okay. So now it was proven by Noether and Lefschetz that actually this Noether-Lefschetz locus is a countable union of algebraic varieties, which is not obvious given my description. A priori, they are only analytic. And then it was proven by Ciliberto, Harris, and Miranda that this locus is actually Zariski dense in U2D. So it is Zariski dense. Actually, it is even dense. This is a result of Mark Green. So again, we are in a situation where there is a lot, tons of exceptional points, and in this situation, the level is 2. Okay. So now, what about? Sure. Yes.
If I wanted to do this in terms of group theory,
yes.
There's some statement like any imaginary quadratic extension gives me a form of GM.
Yes. So you take Q of tau, and the group that you will consider that will be your Manforte group will be the restriction of scalars from Q of tau to Q of the multiplicative group. So this is a subtorus of GL2Q. And the various embedding of that guy inside GL2Q for when you vary all the possible taus gives you all those points. That there are all the subgroups appearing in that case. Again, because GL2 is so small that there is not much place and it has to be reductive. So yeah, it has to be reductive and it has to contain GM because you have to see the weight. So you won't get SL2, for instance. Other questions? Yeah. Yeah, you have to be a bit careful. The level is not exactly 2 in that case. So D large. Okay, very big. I don't want to enter the precise numerology, but okay, and then the case I'm interested in is what happens for n larger than 2. So we have this U and D, and inside we have this Hodge locus of U and D with respect to this variation of a structure, and we know that it's a countable union of analytic subvarieties. But what can we say about that? Until the 90s, basically, nothing was known. Right? So what was the structure? Is it dense? What happens? It's not so clear. It's very difficult to compute. All right, so I will come back to that point in one moment. So now what I want to do is to explain the title of the talk, which is Hodge theory between algebraicity and transcendence. So the first point that I want to emphasize really is that Hodge theory is at heart transcendental theory. It's not algebraic. So let me give some reason for this. So Hodge theory is transcendental, and there is nothing to be done against that. By this, I mean that there is, for instance, so 3 examples. First, there is no purely algebraic proof of the fact that the cohomology of a smooth projective algebraic varieties is a Hodge structure. Okay. So the best you can do is to prove the degeneracy of the spectral sequence Hodge to the RAM, but you will never prove that you get a graduation such that VPQ is equal to VQP bar. Okay, because there is a real conjugation entering the picture. So you will get that VPQ has the same dimension as VQP and this kind of stuff, but never the full statement that this is a Hodge structure. So let's give a second instance of this transcendence. And this has to do with what Javier explained yesterday. So we have seen that basically this Hodge structure is constructed as of comparison from the de Rham cohomology to the Betti cohomology. So to convince you that we have seen on examples that this comparison is not algebraic, in the following sense, if you start with K, a number field realized inside C, then we use this comparison theorem, but now everything is defined over K. So I can take the cohomology of X over K. So now this is a K vector space as yesterday. And the comparison isomorphism that is used even to define the Hodge filtration goes to this. Right, this is this isomorphism that Javier wrote yesterday. And he defined the field of periods as being if you want the field generated by the coefficients of this isomorphism when you write this isomorphism with respect to a K basis here and a Q basis here. So you get coefficients which are numbers in C. And so this is a subfield of C. Okay, this field of period. And now the basic fact is that the transcendence degree of this field is positive. So this is certainly not an algebraic comparison. All right. So that's a second instance of this transcendence. A third instance, well, we have seen it already. I mean, if I have a variation of a structure, then I get my period map. And here, nothing is usually algebraic. This guy is not algebraic usually. And this is a mere analytic map. So we are leaving the nice word of algebraic varieties. Actually, what you can prove is that that guy is algebraic if and only if the level is 1. So which means that basically the idea of studying families of abelian varieties is a very bad idea from the point of view of Hodge theory because you are missing the essential. Although people like that. Okay, so, and you can understand why they like that, because in that case, this space is algebraic. And there something subtle happens, is that in the case where this guy is algebraic, then Borel proves that automatically this map has to be algebraic. Yes? No, it's just It's not a bad idea. It's an excellent idea, but I'm just saying that from the point of view of Hodge theory, you are missing the essential difficulties and the essential transcendence of the theory because everything becomes algebraic. So in some sense, this is nice. For instance, you can develop much more deeply the arithmetic theory, but it means that when you look at usual families of algebraic varieties, which are not, let's say, abelian motives, then the situation is completely different. Okay, so these are three indications that the theory is really transcendental. But now what I want to emphasize is that on the other hand, this transcendence should be severely constrained. So this is not completely random at all. Okay, but this transcendence is expected to be severely constrained. Okay, so yeah. Let's say Javier will come back to that, but let's say the field generated by the period. I don't want to enter that. Okay, so let me explain now this statement. So let's come back to the second point here, which was this comparison isomorphism. So I said that the transcendence degree is positive, but actually, well, you have one of the most famous conjecture in this field, which is due to Grothendieck in '66, which is a period conjecture that tells you that actually this transcendence degree of a Q of this field of period is exactly equal to the dimension of the generic Mumford group, of the Mumford group of X. Sorry. So this comparison is transcendent, but on the other hand, it is controlled by the Hodge theory of that thing. So a second indication that the transcendence is controlled is, of course, the Hodge conjecture. That tells you, remember that I wrote that you have this map, this cycle map to the Hodge classes, so to Fk intersected with H2k xq. And of course, the Hodge conjecture is a statement that these maps should be surjective. So in some sense, those transcendental guys, they should come from something algebraic. And let's look at some consequence of the Hodge conjecture, or at least let me cite Weil. So Weil noticed in '79 in his last paper that actually the Hodge conjecture implies that this Hodge locus for any variation of a structure of geometric origin is not only a countable union of analytic subvarieties, but a countable union of algebraic varieties. And if you think about it, this is really a very strange statement. You have a complex analytic map from the analytification of quasi-projective variety to something which is absolutely not algebraic. Inside this non-algebraic stuff, you have this countable union of analytic subspaces. You pull them back, and they should be algebraic. It's kind of crazy. But this craziness is actually true unconditionally. Or maybe I should say a word. So what is the idea? The idea, you are looking at this Hodge locus. So this means that somewhere in some high tensor power of your fibers, there are some exceptional Hodge classes. Now, if you believe in the Hodge conjecture, those Hodge classes, they come from some algebraic cycle, maybe not in X, but in some product of various X. But then, as I said yesterday, algebraic cycles have the nice properties that they glue together because of the existence of Hilbert schemes. So this means that the locus where this exceptional Hodge class will actually exist has to be the locus where there is an algebraic cycle appearing, but those algebraic cycles glue together along an algebraic subvariety. And so you get that the component of this Hodge locus should be algebraic. All right, so Now you have this remarkable theorem of Cattani-Deligne-Kaplan in 95, saying that actually this is true. That and what is even more remarkable is that you don't have to assume that the variation comes from geometry, from family. It can be an abstract variation of a structure. Is that this Hodge locus is always a countable union of irreducible algebraic varieties of S, which are what we call the special subvarieties. I will come back to that later. But what are those irreducible subvarieties? Well, you have those d prime mod gamma prime inside d mod gamma, and you take the preimage of one of those. The claim is that this is algebraic. Okay. And these are not the special subvarieties. You have to take one irreducible component, and these are the special subvarieties. So the special subvarieties of that shape. Okay, so now maybe I can explain what is the goal of the course. Although I doubt I will have time to really prove. I will certainly not prove everything for sure. I will try to give some ideas how you go there. Is that this is not the end of the story. Actually, we expect much stronger statement. So, so the goal, hopefully in lecture 4, I will try to explain the following result. So what we do, we look at the Hodge locus, and now I look at the special subvarieties whose image in d mod gamma is of positive dimension. And those guys I can study because there is some geometric intuition. It's positive dimension. Also, there is some variational theory. So this is what I will call the Hodge locus of positive period dimension, and just denote it that way. And then there is the embarrassing locus of 0 period dimension. So let me make a picture. Inside d mod gamma, you can have, let's say, a special subvariety. Let's say it's 2-dimensional, this special subvariety. And then here I'm starting from S, and I have my map phi. So the question is, how does the image of that S intersect this d prime mod gamma prime? So it could happen that it intersected in a single point, for instance, like that, in which case I'm in this bad locus because this guy is extremely hard to touch because it's completely isolated. But it could also happen that it touched it in a positive dimensional locus, in which case it's here. Okay. So the theorem that I would like to talk about is the following result with Baldi and Ulmo. Is the following that suppose you start with Z-polarized VHS. So for simplicity, I will assume that there are no product situations from the point of view of Hodge theory. So assume that the adjoint generic Mumford group is simple. Okay. Then the claim is that if the level of this variation is at least 3, then this Hodge locus of positive dimension is actually not only a countable union of algebraic subvarieties, it is algebraic on the nose. So you see that if you look at the moduli spaces of abelian varieties, as I did before, we showed that actually this locus is dense because it contains a locus where the abelian variety splits as a non-trivial product, which is already dense in AG. What we are saying is that as soon as the level is not 1 and maybe not 2, but at least 3, then this can just not happen. There are very few positive dimensional special subvarieties in S. This is just an algebraic collection. I mean, it's just an algebraic subvariety. So for instance, as a corollary of this, you get the following statement for hypersurfaces. So corollary, if n is at least 3 and the degree is at least 5, and then you look at the Hodge locus on this family of universal family of hypersurface, let's say for the primitive cohomology, and I take the positive dimensional part of that locus, this is algebraic. So what I want to explain now is the tools that you need to produce this kind of thing. Finiteness of this is exactly, well, you have to be careful. So there are finitely many maximal components. This means that there could be a lot of components of smaller dimension with smaller Manforted group, but they are contained in finitely many maximum ones. And of course, it says nothing about possibly isolated points. But the conjecture is that actually the full Hodge locus in that case is algebraic. So what I want to explain, I will come back to this in the last lecture, is a heuristic towards this kind of result, which has to do with atypical intersections. And what I want to do now and tomorrow, so today I want to explain one basic tool, which is tame geometry. And tomorrow I want to explain a result in functional transcendence that are used to prove this kind of stuff. So, and in that case, we even know that they are defined over Q-bar. Yeah, this is a result of myself with Anya and David Urbanek. As also expected from the Hodge conjecture, but I don't want to talk about this arithmetic aspect. There are, but finitely many. All right. Okay, so let's move. Are there any other questions before I move on? Yeah. No, it's for any. So this is what I want also to explain, is that in some sense, getting rid of all algebraic geometry makes you focus on what is more important, which is in that case atypical intersections. So this is a very good question. I don't know of any motivic explanation for this, but I have to discuss with Joseph Ayoub much more to try to understand if what is the form of. There should be a motivic Griffiths transversality, but I've never seen it described very precisely, actually. Yeah, I should say that everything at the end, so the level plays such an important role because of this Griffiths transversality. But yeah, sure. Of course, no. This is, well, in that case, in some cases, you have some idea, but in general, no. You just get a nice finiteness statement. You even can say that those varieties are defined over Q-bar, as Javier remarked, but that's it. Other questions? Okay, so let's move to tools. And in some sense, what I want to do now is make some overview of the tools that are used in this thing. But I think the tools are even more fun than the final results. So I really want to convince this, at least the tools from today. Tomorrow, functional transcendence, well, it depends on your taste. But all right, so so I actually start lecture 2, so you see that I'm very late. So Hodge theory and tame geometry. So all this business started first in the case of Shimura varieties, but actually I got interested in this thinking about, okay, those period maps are supposed to be just complex analytic. And nevertheless, we get this incredible result of catenating Kaplan, that the pre-image of all that this phi minus 1 of d prime mod gamma prime are algebraic. So how is it possible? And the idea is that such analytic maps, they should be almost algebraic, or at least have the nice topological properties of algebraic maps. And maybe they are very tame. So let me make a crash course on tame geometry. So this has nothing to do a priori with algebraic geometry, not even complex analytic geometry. This is really, well, this is geometry over R. So the idea of tame geometry was introduced by Grothendieck in Esquisse d'un Programme in 1984. And the idea of Grothendieck is that you want to get rid of all the pathologies that are developed when you make a course on general topology, because for him, those things do not exist. They were created by analysts for the use of analysis, but actually they never appear when you study shapes of natural forms. So of course you want to get rid of Cantor sets, piano curves, this kind of thing. But the typical guy you want to get rid of is the following. So what is the monster you want to kill? The monster you want to kill is the graph of x gives sine 1 over x for x positive number. So this very rapidly oscillating function. So why do you want to kill that guy? For at least 3 reasons. First, that guy is a typical example of a connected set, which is not arc connected. So from the point of view of geometry, it does not exist. I mean, by this, I mean the gamma bar. The closure of this, so this is this interval, and you have this very oscillating, fast oscillating function towards it. So this is this vertical interval union gamma. So as I said, this is this is not arc connected, but this is connected. So this is not a geometric object because you have to lift your pen to draw it. Well, even doing this, I cannot draw it. But anyway, why is it really bad? Well, because whatever kind of dimension you want to define, the dimension of the boundary, which is that guy, is 1. And the dimension of the graph is also 1. So as soon as you have this kind of phenomenon, there is no way of doing stratification theory in any meaningful way. And if you have no stratification theory, you have no geometry. That's basically the idea. The third reason why this is really bad is that if you look at the intersection of gamma with the real axis, then it contains infinitely, it's not a finite type. So you need too much information to describe it because you're crossing infinitely many times this axis. So it's not a very natural object. So starting with that, Grothendieck decided that there should be a much better way of doing geometry. And what should be the prototype of algebraic geometry? Well, the prototype should be, you would like to have a geometry where you have all the nice properties of real semi-algebraic geometry. So the prototype is really a real semi-algebraic geometry. So I don't want to recall anything about that, but the basic idea is that if you have a semi-algebraic set, then its closure is also semi-algebraic. The boundary is semi-algebraic. The dimension of the boundary is strictly smaller than the dimension of the set. Any semi-algebraic set has finitely many connected components, so this kind of intersection with the real axis will never occur. Any connected component of semi-algebraic is semi-algebraic, and you have a nice stratification theory. So what you would like to do is to do exactly the same thing, but in a much more general setting, because of course semi-algebraic is too close from algebraic. And the way to do it, well, it was not clear when Grothendieck wrote his proposal, but it was developed in one direction by logicians, actually model theorists, and under the name of o-minimal structures. So you should not be frightened by the name, not by the words model theorist. I know nothing about model. I know very little of model theory. But what is nice is that you can define it purely axiomatically and using only basics of general topology. So let me first define what is a structure. So a structure for us is just a collection. This is, you give yourself the collection of sets you are allowed to play with, and you just put a few axioms. So it's a collection S of subsets of sets Sn. So Sn is a set of subsets of Rn, which are the subsets you are allowed to play with. So what are the requirements? Well, first you want all algebraic sets. So algebraic sets of Rn belong to Sn. Okay, so at least it's not empty. Second, you want stability on the product. So if A is in SP and B is in SQ, you want that A times B is in SP plus Q. Third, a purely logical constraint, you want Sn to be a Boolean subalgebra of the power sets of Rn. So you want Sn stable under intersections, finite unions, and complements. Okay, so up to now, everything is more or less formal. So the fourth axiom is important. The fourth axiom tells you that you are stable under linear projection. So you want that if P from Rn plus 1 to Rn is a linear projection, and if A belongs to Sn plus 1, then this implies that P of A belongs to Sn. And now you see that this becomes kind of ugly, because suppose I give myself a structure of to dimension 2000, right? And in dimension 2001, I decide to introduce a new set in my structure. But then this means that all the linear projections of that set becomes automatically part of the structure. And if you are not very careful, very fast in dimension 1, you will get a counter set. So it's clear that this is not a very good definition for doing geometry. It's a purely set theoretic definition up to now. So we'll see that this is, of course, not enough. So we will call the S-definable sets are precisely all the subsets in all the Sn. And now if I have a function from A to B, I will say that it is S-definable if its graph is. So in particular, A and B, so this is in Rn, in Rq. So this implies that A and B have to be definable subsets, S-definable subsets of Rn and of Rq, and the graph in Rn cross Rq has to be definable. So, okay, this is just a way, axiomatic way of giving yourself the collection of sets and functions you are allowed to play with. So a typical example, what is called R-alg. So this is the simplest structure, and actually any structure contains that one. So the definable sets are just the semi-algebraic sets. You see that the algebraic sets do not form a structure by themselves because of axiom 4. The projection of an algebraic set is not algebraic, but it is semi-algebraic. And now semi-algebraic sets are stable under linear projections. This is Tarski-Seidenberg theorem. So the semi-algebraic sets. And because of the first axiom, any structure will contain that one. Okay. So now an important point is that basically you can give yourself any collection of sets and maps and define a structure out of this just by taking the smallest structure containing all those guys. The reason being that you see on the axioms immediately that the intersection of two structures is a structure. Okay, so it makes sense to talk of the smallest structure containing a given collection of sets. So for instance, this means that you can define Rx. So this is the smallest structure containing the graph of the real exponential. You can define the structure Rsin, which is the smallest structure containing the graph of the sine. And this one we don't want. So we have to get rid of, yes. Sorry? I wrote under intersections and finite unions. Yes. I don't want to discuss this now. This is fine. No, any intersection is fine. Okay. I don't get. Another structure is Rn. So this one is more interesting. This is a structure where you allow any real analytic function in restriction to a box 0, 1 to the n. So you don't allow all real analytic functions, but real analytic functions on compact sets. So now, fun exercise. So exercise, if you want to do it, is that if A is definable, then A bar, the interior of A, and the boundary of A are definable. So when you fix a structure and write definable for definable in that structure, you can prove that if f from A to B is definable, then f of A, f minus 1 of B are definable. And that the composition of definable functions is definable. And here you use something non-trivial, is that the Euclidean distance is given by a quadratic form, which is a polynomial. It's semi-algebraic. Okay. All right, but we see, as I explained, that this is not a very good definition to do geometry, because this is purely set theoretic. In particular, we already know that we don't want this R sign structure for doing geometry. And then the idea of model theorists was very simple, is that an O-minimal structure is a structure with a fifth axiom. And the fifth axiom is just that you counterbalance the axiom 4 that creates a lot of sets by a fifth axiom that tells you that in dimension 1, an element in S1 is semi-algebraic. In other words, this is a finite union of intervals and points. And you see that those two axioms, they play one against the other. As I said, if in dimension 2001 I create something very complicated, this fixed axiom tells me that I cannot do anything I want. I have to be careful that when I take all the possible linear projections, then in dimension 1 I get nothing else than semi-algebraic. So now, to give you a flavor of why this gives you a tame geometry, I want to state a few fundamental results. So the first fundamental result is what is called monotonicity theorem. Maybe I should give an example. Of course, R alg is o-minimal, and R sin is not. Because the locus of 0 of the sign, I get an infinite collection of points. This is not semi-algebraic. Okay, that's good, but that's not enough. I mean, as I said, we want something more than semi-algebraic. Yes? The locus of zeros, I look at the zeros of sign x, I get an infinite collection in R. So this is not good. So this result describes definable functions from an interval to R. And this is absolutely basic. So suppose you are definable. And now by definable, I mean definable in some o-minimal structure. All the structures now will be o-minimal. Then the statement is that there exists A0 smaller than A1, a finite collections of points in AB. So A0 will be A. AN will be B, such that F in restriction to AI plus 1 is continuous and either constant or strictly monotonous. So you see that a definable function on interval is very special. It cannot oscillate infinitely many times because you know that there is a finite partition such that it is either constant on one piece of the partition or strictly monotonous. Okay. And here I can force it to be continuous, but I could fix any order of differentiability and get the same theorem. Of course, you have to change the partition, but you can prove the same result for any CP. For C infinity, this is false. There exist o-minimal structures where this theorem does not work with C infinity. But for each finite P, CP is fine. So that's the first basic result in this theory. And the second basic result, which makes everything work, and the proof uses that one, is what is called the decomposition theorem. Not perverse shapes here. Is that you give yourself A1 and AK in Rn definable in some o-minimal structure, is that there exists a finite cylindrical cellular decomposition of Rn such that each AI is a union of cells. So let me describe what I mean by a cylindrical decomposition. Well, in dimension 1, this is completely clear. So in dimension 1, you just take R, you fix finitely many points. What are the cells of this decomposition? Well, you have the points and the interval. Okay. This is what I call a cylindrical decomposition. Now, in higher dimension, the definition is by induction on the dimension. So basically, you build tubes over such things in dimension 1 less. So a cylindrical definable decomposition of Rn, well, you give one of the Rn minus 1 plus for each cell C of Rn minus 1, the picture is the following. You give yourself, so you have your cell C, you give yourself finitely many continuous definable function on C, such that one is strictly bigger than the previous one. So this will be FCI, which will be strictly smaller than FCI plus 1. Okay. And then what are the cells? Well, the cells are the bands here in Rn and the graph of the functions. And you have finitely many such functions over each cell. So this is why this is called cylindrical. You have the basis Rn minus 1, you have your cell decomposition there, and above that cell decomposition, you construct tubes. And on those tubes, well, you construct bands and graphs. Okay, that's very basic stratification theory. Yeah. No, they do not for many reasons. They are not first. They do not even define the structure. Because if you take analytic sets and you take projections, these are not analytic. So you have to take sub-analytic. But then sub-analytic, this is complicated because a good definition for sub-analytic, you need to project something bounded, because otherwise this is really ugly. Think of something analytic going to infinity, and then you project it in dimension 1 less. This is certainly not anything reasonable. So you have to project on some bounded piece. So you have to define what are called globally subanalytic subsets, which means that they are not only subanalytic locally, but even at infinity too. So I don't want to give the very precise definition. But the consequence of that decomposition theorem is that if A is definable, then you see immediately that because this is a finite union of cells, it has finitely many components, connected components already. And any connected component will be definable. And the dimension of the boundary will be strictly smaller. Because here it's clear on the band, the boundary are those guys and so on. So you get all the nice topological properties that you liked. So now what is important is to know that there exists some o-minimal structures more interesting than R-alg. So examples, well, you have Rn. So this is the structure generated by all functions from -1, 1 to the n to R, which are real analytic. So here you are allowed to play with real analytic functions, but only on compact sets. And the definable subsets are exactly what you mentioned, what I mentioned to you. These are the globally subanalytic subsets. And basically, the fact that this is o-minimal follows from a famous result of Gabrielov that tells you that if you take a subanalytic subset, its complement is also subanalytic, which is absolutely non-trivial. Then more interesting, and this is absolutely crucial for us, is that if you take this monster for an algebraic geometry, which is a real exponential function, Rx is o-minimal. And this is fantastic. This is why we managed to get out of algebraic geometry. So this is the famous result of Wilke using the proof uses some model theory. Nowadays, we can get rid of model theory, but it builds on fundamental result of Khovansky. So let me maybe mention this. What is a Khovansky result in a very basic form? It tells you the following. Suppose you consider the set of solution of a polynomial in n variable, in 2n variable, but of the form x1, xn, and then exponential x1, exponential xn. And look at such sets. Then Khovansky theorem tells you in particular that such an equation define the set of solutions has only finitely many connected components. And if you try to prove this, good luck. I mean, this is really hard. And this is a basic tool to prove that this structure is o-minimal. But then this is fantastic. This means that in this structure, for example, you get you will get a function like x to the power alpha or exponential -1 over x. I mean, when you do a classical class in analysis, everybody tells you that exponential -1 over x is very nice when x goes to infinity, right? Surely, I mean, you see that it's really going, it looks like a really decent function. And it is, because it is in this structure. And so you get x alpha for alpha irrational in this structure. This is a function which is definable. You get exponential -1 over x for x positive, and so on. Now, something that will be exceptional but very helpful is that actually, if you look at the structure generated by those two structures, it is still o-minimal. So this is very far from true in general. If you take two o-minimal structures and you take the structure generated by those two guys, it's almost never o-minimal. But in this case, it is. So actually, the entire structure that we want to use is Rnexp. And it is o-minimal. So here, I'm allowed to use the full real exponential function and other real analytic functions, but only defined on a compact set. Okay, so I'm very late, but maybe I want to relate this now to Hodge theory. So what time is it? Yes, so let me state the main result, and I will explain tomorrow why this is important. Even if you maybe don't see it. So let's come back to variation of a structure. And let's look at this associated period map. So as I said that this is a complex analytic map, almost never algebraic. So the theorem is the following. So due to Baker, myself, and Zimmerman. Well, there are two parts. One, which is purely group theoretic, is that D mod gamma has a factorial R-alg structure. Here I should be a bit careful. So Up to now, I'm working only with subsets of Rn. But of course, I can globalize. So let me try to describe what is a manifold definable in an o-minimal structure. It means I can find a finite atlas of charts. Finite is crucial. I want to keep all the finiteness properties. So a finite atlas of charts such that the charts maps to definable sets in Rn, and the change of the intersections of two charts maps to definable subsets of Rn, and the change of coordinates are given by definable maps. Okay. So what I'm saying is that D mod gamma, which is a manifold, has a functional R structure in that sense. Namely, I can find finitely many charts of that space, which are semi-algebraic, and such that the change of coordinates are semi-algebraic. So it's not a real algebraic variety, but still it has a canonical semi-algebraic structure. By functorial, yeah, I will take your question, but in 1 second. By functorial, I mean that all the D prime mod gamma prime inside that D mod gamma are definable. Yeah. The other charts will be, but what is very important is I can find a complete cover by finitely many. Because after that, each time you want to argue chart by chart. But of course, if you want to keep finiteness, you need to be able to cover everything only by finitely many charts. So this is the first part, and this is purely group theoretic. And the key word here is Siegel sets. Now, what is the true theorem? The true theorem is that okay, now you look at that map. It has an RL structure. This guy is a complex algebraic variety. In particular, it is real algebraic if I look at it by restriction of scalar. So it has also a real semi-algebraic structure, canonical one. Now, the claim is that if I extend the structure from Rn to Rnx, this map is definable in Rnx. So B is that phi is Rnx definable. So one way of saying it is I start with this quasi-projective variety. I choose a covering by finitely many affine subschemes. Okay. When I take the restriction of the affine subschemes over R, I get a real algebraic set. And in those charts, and if I read that map in the charts of D mod gamma defined by part A, well, the map phi can be written using only the full real exponential function and real analytic function in restriction to compact sets. Nothing else. Of course, polynomials and so on, and that's it. So that's a statement. So, okay, tomorrow I will explain because once I will finish this lecture tomorrow by saying that once you have this theorem, Kaplan theorem, the proof is in 3 lines. Okay, but of course I'm cheating because to prove this we use some of the tools used in Kaplan, although we do not use all what they needed. Okay, so I guess I stop here. Sorry for being late.
Okay, thanks a lot. Questions or comments?
Will you give some idea of why B is true?
Yes. So it was planned to be done. All right. So maybe what I want to do. Okay, let's do it just maybe for in the case of moduli of elliptic curves. So, for example, you have Sn and you have this period map that actually is an ISO between H with H modulo SL2Z, right? But now the two real algebraic structures are completely different. Here, this is the real algebraic structure coming from the interpretation of S as being a moduli space. So this is a scheme. Now I would have to describe you what is the semi-algebraic structure that I put here. And the semi-algebraic structure that I put here is that here I have the map from H, and inside H I can choose a fundamental domain, and I choose a standard one. So I have this fundamental set for the action of SL2Z. This fundamental set is semi-algebraic. And basically what I'm saying is that I identified that guy with that guy, and this is the semi-algebraic structure that I put on H modulo SL2Z. Of course, you have to be a bit careful what you do because there is a finite redundancy here, but this is what I'm doing. So now the statement can be seen by saying that if I look at the inverse map, which is the J map, what I want to prove is that the map J restricted to this fundamental set F is definable in R and X. So here we know that from the moduli point of view, that thing is just C. Okay, that I think of as being R squared, of course. So what I have to prove is really that this map is essentially given just by a real exponential. I am not allowed to use complex exponential, of course, and polynomials and real analytic functions restricted to compact sets. But now let's make just a small picture. What happens if you start with this fundamental set? So that guy here is that what you can use, you can factorize it through using exponential 2 pi I dot. So what happens? Well, let's do it maybe on some set like this. I can do it on a smaller set if I want. But anyway, what happens is that I'm mapped to a punctured disk. Okay. So here, of course, I'm using the coordinates x and y. So you see that if I take a point x plus iy, what I get exponential 2 pi I x. And this is bad because it is real analytic, but it's not allowed. This is not an exponential because essentially I will have a sign. But I really don't. Well, let me write explicitly. This is exponential minus y, and then I get cos x plus I. Well, there is 2 pi plus I sine 2 pi. And this does not look definable, but it is, because here x on f is bounded. So these are real analytic functions on a bounded set. So this is a definable map. So you see that the problem with this factorization, if you start from the universal cover, is essentially the periodicity under the action of gamma. So a periodic function can never be definable, but as soon as you restrict to a fundamental set, maybe you are lucky enough, and this is what happens here, that this map becomes definable. So this is a basic fact. The complex exponential is not definable because you have sine and cosine in it. But if you restrict it to a bounded set on the abscissa, then it becomes. So this is definable in Rn. This is definable in Rexp. And so this product is definable. So that map is definable. And now the J function here, you are going to see, but C is inside P1C, and the punctured disk is inside the disk. And basically, what you can easily show, this is classical, is that this map, which is here, extends meromorphically. So actually here, this is algebraic. Okay. In restriction to some compact set anyway, so I'm done. So that's for the J function. The problem is that if you go to a higher dimensional Shimura variety, of course, you are completely unable to write explicitly the uniformization. So then you have to move to much more group theory. This is what we did with Ulmo and Yafaev 6 years ago, where we proved that the uniformizing map restricted to some fundamental set for a Shimura variety is always definable in R and X, just using group theory. And then basically this theorem B for any period map, well, it's just much more complicated. You need the full power of degenerations of Hodge structures and so on. But that's the idea. Although it looks like a miracle, I have to say, but that's how it works. Other questions?
Okay.
It seems like o-minimal structure is purely topological. Is it true? Like if you have a
So it's not purely topological. Actually, what you are using is really the order on R. This is where the O comes from. O comes from order. So actually, you can define such a theory on any real closed field, for instance. And it has not been used so much right now, but I'm sure it should have some applications. In particular, you can use it on Q bar intersected with R.
So for instance, if I have some analytics analytic scheme, then it can see reduced structure, or is it?
Well, if your analytic manifold is compact, then it is automatically definable in Rn, because complex analytic is in particular real analytic, and if you restrict yourself to compact, then you are definable in that. But what is important is for non-compact complex analytic space, and the definable one in Rnx are very special. And this is what happens here. This D mod gamma is, but you can easily construct examples which are not, and so on and so forth. And as soon as you have a complex exponential without any kind of periodicity, like the one you have here under the action of SL2Z, then it will never be definable in some o-minimal structure. So is something really happened, but what precisely? It's kind of complicated. Yeah.
So so it really looks kind of like Tate curvish.
Like what?
Tate, like the Tate.
Yes, it's very similar. It's actually, this is the same kind of uniformizations.
And is there anything beyond?
Right. I mean, in the Tate curve, you are already here, but you don't go upstairs. You start from that and uniformize by Q to the Z. Yeah, so there should be a p-adic theory, but right now it's not yet fully developed.
All right, so it's the last talk of today. So it's my pleasure to introduce Javier Fresán, who will lecture about periods, motivic Galois groups, and the Kontsevich-Zagier conjecture.
Thank you. So recall last time I introduced the comparison isomorphism. So the situation was X, so smooth variety, which is defined over a subfield of the complex numbers. And then there was a functorial isomorphism from algebraic the rank homology of X, tensor C, to Betic homology tensor C. And this isomorphism was given on affine varieties by integrating differential forms on smooth chains. Okay, so the first thing I'm going to do today is to finish my lecture from yesterday. So I wanted to give you an idea of how to prove that this map is an isomorphism. But before doing that, let me give you an exercise, which was stated in Bruno's talk before. So let's consider K inside the algebraic numbers. Let's assume X is projective. So he said that when you consider the field generated by the periods of X, let's say the periods of Hn of X. Okay, so this is the field generated by all the coefficients of a matrix of this comparison with respect to some K basis here and a Q basis here. So he said the transcendence degree of this field is positive. Well, it's projective, the dimension is strictly positive. And one way to see this is that this field contains a power of 2 pi I. And more precisely, it contains 2 pi I to the power n times the dimension of Hn divided by 2. You see that this is an even number by Hodge theory. Okay, so if n is odd, the dimension of Hn is even. When you divide by 2, you get an integral power of 2 pi I, and this will be inside this field. So the exercise is to prove that that this is true, and the hint is to compute the determinant of this comparison isomorphism. So the determinant is well-defined. No, it's a well-defined element modulo K star. Okay, because it depends on the choice of the basis. And then the statement is that it is essentially this. So if you want to be very precise, there exists some element alpha in K, non-zero, such that this determinant is equal to a square root of alpha times this power of 2 pi I. Okay. And how will you prove this? You will prove it using the favorite theorem from Geordie's lectures. Okay, so let me try to give you an idea of how to prove the comparison isomorphism. So some parts of the proof we already saw in Bruno's lecture. So, well, it's going to be a change of isomorphism. So first we start with the ramp cohomology of X. So this is a K vector space. And when the ramp cohomology is compatible with extension of a scalar. So this actually is going to be the same thing as the ramp cohomology of X scalar extension to C. Okay, so this means X over C. Okay, so from this first step, you can consider that your field is equal to C. And then the crucial step in the proof is to consider an analytification map. Okay, so this was defined as the hypercohomology of the sheaf of Keller differential. So these are differential forms with polynomial coefficients, but you can consider the same thing with analytic coefficients. I'm going to denote it like this. So this is the hypercohomology of the complex of sheaves, where now the differentials are in the sense of so this is a complex manifold, so it's in the sense of complex analysis. So the coefficients will be holomorphic functions. Okay, and then here you have Poincare lemma. So actually this holomorphic complex, maybe let me write it here. So you have the holomorphic complex. And you can consider the sheaf of locally constant functions inside, and the Poincare lemma tells you that this is a quasi-isomorphism. So here, this will be the same thing as the topological space X of C, homology of the constant sheaf. So this is Poincare lemma. And then, well, there's another resolution of the constant sheaf C, which is given by the complex of singular cochains, if you think of them as a complex of sheaves. And then this gives you another isomorphism where what you get is the singular cohomology. Okay, so in principle, you get it with complex coefficients, but then you can use the universal coefficient theorem to take the coefficients out of the group. So what you get is this tensor C. Yeah, so this is okay. And if you analyze well what's going on here explicitly, and then this is a very good exercise, you will see that this map is given by integrating differential forms on smooth chains. Okay, so the work in the theorem is actually to prove that this analytification map is an isomorphism. So this is the real content of the theorem. Well, I have nothing against Poincare lemma; it's very nice, but this is the hard part. Yes. The composition of the two. Yeah, you should think of C that goes to the rank complex and to the singular cochain complex, and well, the composition of one map with inverse of the other, which is a quasi-isomorphism. This is the one given by integration. Yes. Mm-hmm. It's a good instinct. It is a good instinct. No, this is what you do. You will compute the square of the determinant using the pairing on Hn given by your integration. Is it okay? Okay, so well, we need to prove the analytification map is an isomorphism. And in the situation where X is proper, we already saw in Bruno's lecture how to do this. So this is a consequence of Gaga's theorem. And the reason is that, well, in both cases, you can compute the spaces using a spectral sequence. So in the algebraic situation, the spectral sequence is HQX omega p. In the analytic setting is the same thing with analytic. I will forget C very often, I think. With analytic X and holomorphic differentials. And now this shift is the analytification of this one. These are coherent shifts on a proper variety. So Gaga's theorem says that this is an isomorphism. And this isomorphism is compatible with the differentials because, well, the differential of an analytic form is the same as the computed as an algebraic or as an analytic form. So you get an isomorphism of a spectral sequence, and then you get that these two are isomorphic. Okay, and this is the proof for X proper. And of course, this proof fails if X is not proper. So fails. For example, if X is the affine line, and this is also very related to Bruno's course. So here for H0 of OX, you get polynomials with complex coefficients. And in the analytic situation, you get all entire functions. So it is not true that these spectral sequences are isomorphic, but the result is still true because this map is an isomorphism because, well, the polynomials with zero differentials are constant, and every polynomial is the derivative of a polynomial. So you get that the cohomology is C in degree 0 and 0 in all degrees. And here is the same thing. An entire function with zero derivative is constant, and every entire function has a primitive. So what to do? So if X is not proper, so I'm going to explain a proof which is due to the linear. So the linear proves a more general result, where here you actually have the cohomology of any vector bundle with connection with regular singularities at infinity. So this is proof in his lecture notes about differential equations. And if you look at the proof and take the trivial connection everywhere, this is the proof you get, the one I'm going to present. Okay, so the idea is to compactify. So we compactify. And we try to compute the cohomology on a compactification where we can use Gaga type results. And well, the easiest situation would be if you could compactify by a smooth divisor, and then you will compute the cohomology. Everything will be smooth, and then you will compute the cohomology of X in terms of that of the contractification and of the smooth divisor at the boundary. So exercise. If you consider C star square, this does not have a compactification by a smooth divisor. Okay, so the most appropriate proof for this summer school is the one using what you learned in Heinloth's talk this morning. So it's a Hodge theory argument that shows that this is not possible. But Mirko explained me also a proof where you don't use any Hodge theory and it's more about birational geometry of surfaces. Okay, so this is not possible, but the next best situation is possible. And this is something that follows from resolution of singularities. Which is that there exists a smooth, proper variety X bar and an open immersion of your original variety into X bar, such that the complement is a simple normal crossing divisor. So this means that D is locally like the union of a number of hyperplane coordinates in C to the n. So recall. So the inside X bar is a closed subvariety of codimension 1. And for each point in D, there exists well, a system of coordinates X1, X2, the D in the maximal ideal at P, such that D is defined by X1, X2, the R is equals to 0 for some R between 1 and D. Okay. And then this implies that all the irreducible components of your divisor are smooth. And when you take intersections of M of them, you get a smooth subvariety of codimension M. And then you can just work with all these irreducible components. Combinatorics is a bit more complicated, but it's almost as good as having a smooth divisor. Okay. And once you have this compactification, you can, instead of working with the sheaf of Keller differentials, you can consider what are called logarithmic differentials. So this is a subcomplex of the direct image of omega of X. Okay, so these are forms with poles of any order at D, and essentially here you take those with logarithmic poles. So it means it's the smallest subcomplex, which is stable by wedge product. Contains well, those differentials with no poles. So Keller differentials on X bar. And it also contains all things of the form df over f for f function that does not vanish on X. And then you can, well, you can prove that omega 1. So in terms of your equation, this will be locally generated by dx1 over x1 up to dxr over xr, and then the rest of the coordinates. So it is still locally free of rank the dimension. And omega p is just the pth wedge power of omega 1. Okay. So this is the algebraic version of the story. And then there's an analytic version where you take essentially the same definition that you have local analytic coordinates as that it is like a union of hyperplanes. But there's just a small difference you need to put into the definition that the irreducible components are smooth. Doesn't follow from. So analytically, something that like this, here you will have this kind of coordinates. And then the key statement that makes the proof work is the following. Is that if you consider the analytic situation, so you have the sheaf of holomorphic differentials on X. Inside you have those with logarithmic poles. And you have something in between, which are those meromorphic differentials. So these are meromorphic differentials. Okay, so if you compare with the algebraic situation, what happens is that there could be essential singularities at infinity. So actually, when you take this sheaf and you analytify it, you don't find this. So there could be essential singularities at infinity. What you find is this one. Okay, so you have this, yes? Which one? This? The holomorphic differentials on X that have any kind of behavior at infinity. You don't say anything about infinity, and here you say that they are meromorphic at infinity. Any pole order, and those are order one, yeah, exactly, yes. Everything proposition omega x bar n dot log d n g lower star m for meromorphic omega dot x n and then j lower star omega x n dot. Okay, and then the proposition is that these inclusions are quasi-isomorphisms. So maybe a quick idea. So you should do this in dimension one, and then in higher dimension, the proof is essentially the same, but much harder to write because of notation. But you will get the idea. So in dimension one, well, it's a local statement. So you just need to take a point of D and work locally around. So you can take a ball such that the intersection with with D is Z equals to 0. And then, for example, the inclusion from logarithmic differentials to everything. So on this ball, this will be, so you consider this one. Yeah, so. So you have the inclusion here. And the idea is to prove that this inclusion is a homotopy equivalent. So you need to write down a map in the other direction such that the compositions are homotopically equivalent to the identity. So what is this? This you have in degree 0, you have power series, A and Zn, n is an integer, and on degree 1 you have something that you can write like this. So Bn set to the n dc2 over c. N is an integer. And the idea is to consider the map that forgets the non-polar part here. Okay, so you will consider a n set to the n is bigger than 0, and Bn set to the n, d set to the n is bigger than or equal to 0. And well, you do the exercise to prove that this is, so exercise, let's call this iota, this is R. So what is clear is that iota composed with R is the identity. So you need to prove that R composed with iota is homotopically to the identity. So try to do that. Okay, so once you know this, let's do the proof. So we have algebraic de rank homology. So this you can compute on the compactification. Okay, so this is the Lerre spectral sequence. Now the complement of a normal crossing divisor has this nice property of being an affine morphism. So this is actually exact. So here you get the same thing as x bar j lower star omega. So j is affine. So now you can use we are on a proper variety now. So you can use the Gaga theorem. This is not coherent, but it's quasi-coherent. So Gaga is a limit of coherent shift. So Gaga is still true. So this will be isomorphic to the analytic homology of the analytification. So the analytification, let me recall you, are meromorphic differentials. Okay. So now you use the proposition. This is the same thing as all differential forms, maybe with essential singularities at infinity. And again, J is well the algebraic and the analytic analog of affine. So it's Stein. It's a Stein morphism. So this is the same thing as the derived image. And then this is, oh, sorry, this is X bar everywhere. I'm sorry. And then this is the same thing as the analytic, the ramp homology. Okay. So this is how the proof goes. And a corollary of this proof. So you may wonder why I introduced the sheaf of logarithmic differentials. So one corollary of the proof . Yeah, here I use J, the morphism J is Stein. So coherent shifts have the J lowest is exact on coherent shifts. And a corollary of this proof is that H the RAM algebraic, at least over C, it is actually isomorphic to the cohomology on X bar of the logarithmic, the rank complex. Okay, because at this step, by the proposition, this is also the cohomology of the sheaf of logarithmic differentials, which is the analytification of the algebraic one. So you also get this isomorphism. And you can, of course, prove this isomorphism algebraically, but the proof is more complicated because you don't have, I mean, you need to work at least maybe with étale coordinates. You cannot reduce to the nice situation where you have a ball and then the functions are just power series. Okay. And from here, you can say you can see several things. One of them is that this is finite dimensional. Space. I told you that I will explain an algebraic proof. So the proof is that you are computing this as a cohomology of a complex of coherent sheaves on a proper variety. So those are finite dimensional. Yes. 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 Which one? Yeah. So this one, these are analytic differentials on X, which is the same thing as the analytification of algebraic differentials on X. But then you consider you just push forward, and then you lose control at infinity. So exactly. So algebraic things, when you analytify them, you only get poles. Okay, so this is I promised an algebraic argument for I didn't really give it, but you could do it this way. And the second important consequence is that you can use this to get the mixed Hodge structure. So we saw a lot the Hodge filtration in Bruno's talk. So the Hodge filtration, you get it in the same way you consider the truncation of this complex. So FP will be the image of this complex where you start in degree P. Okay. This is also computed as the cohomology on X of the complex of Keller differentials. So you could take the filtration there, but that's a bad idea. This doesn't give the good filtration because it's vanishing for affine varieties, this kind of phenomena. So you should do it on the compactification. But now there is a new phenomenon here, which is the weight filtration. And this comes from the filtration given by the order of poles. Okay, so this sheaf of logarithmic differential, it has a filtration which is in positive degree. And in degree 0, you consider differentials with no poles. And then you add one step by step, you add the possibility that there is one pole in the wedge product. So this is what you get. 0. And just everything. Okay, so you can filter by the order of pole the complex, and then this filtration on cohomology. Yes, thank you. So the weight filtration on the rank cohomology will be the image of this filtration. Except that, well, you want the weights to start in degree n. So you should shift it a little bit. So it will be omega w n minus n omega dot x bar log d. Okay, so for example, if m is equal to n, you get omega 0. Omega 0 is Keller differentials on x bar. And then it says that omega n of hn is the image of the cohomology of x bar, which is what we saw in Jochen's talk this morning. And an important point in the theory is that, well, this is on the RAM side, and you also have a weight filtration on the Betty side of the story, which is defined over Q, and it is the so on the Betty side. Not going to write the indices, but so this is the filtration given by the LRS spectral sequence for the inclusion. So it means you compute the cohomology as the cohomology on x bar of R J lower star Q. And then this puts a filtration, and then this filtration corresponds to the other one by the comparison isomorphism. Okay, so this is the end of yesterday's lecture. Are there any questions? Yes. Which one? Here with the logarithmic. Yeah. It means when you have a x and a map to y and a complex of shifts on x, you can compute the cohomology of the complex on x as the cohomology on y of the direct image. No, you don't need for the isomorphism. It's a general thing for the isomorphism. Of course, if you know that the general is, you can get much more precise information. Okay, so next thing I want to do is yesterday I gave you a definition of periods, but I said it was tentative because I was only considering integrals over closed cycles, and then there are things like the logarithms where you need to integrate on something with a boundary. So this is solved using relative cohomology. So let me very briefly talk about relative cohomology. So relative means that you have your variety X as usual, but you also have a closed subvariety that I'm going to call D, because most of the time it will be a simple normal crossing divisor. And then you have two flavors of it. So Betty homology and cohomology as usual. Let me do homology, which is so H Betty XD. So this is defined. You look at the complex of singular chains on D, the complex of singular chains on X. You have the map induced by the inclusion, and you take the cone. Okay, so this is the cone of the map induced by the inclusion. So this goes from a complex of singular chains of D to the one in X. And you consider you consider the cohomology of in degree, maybe the homology. It's a homological complex in degree n of this cone. So concretely, I don't need to write down what this means, but very concretely, this means that every class here is represented by some sigma, where sigma is a singular n chain on X. So in usual homology, the condition is that there's no boundary. Here, the condition is that the boundary is a chain in D. meaning that it lies on the image of the inclusion map. Okay. And then you have a long exact sequence. So you have the cohomology of D, and this goes to the cohomology of X. And then you go to relative homology. And then you can consider the boundary that goes to Hn minus 1 of D. So this is just the inclusion. Here is the map that sends, well, if a class has no boundary, in particular, the boundary is contained in D. So, and then this is the boundary map. Okay, so. And then there's the RAM version of the story. So if your subvariety is smooth, you can do exactly the same thing, because we know what the RAM cohomology of smooth varieties is. But this is not enough for the applications to periods. So you really need to consider the case where D is a normal crossing divisor, simple normal crossing divisor. And then it gets a bit more involved, but well, it's not too bad. So the idea is to use that all irreducible components are all intersections between them are smooth varieties. So you form a big double complex, and then you take the cohomology of the total complex. So it will be something like this. So you have the OX, omega 1 of X, and so on. Here you have restriction maps to the irreducible components. Now you go to intersections of two components. And so on. You need to put appropriate signs everywhere so that things give you complexes. And then you form the total complex by consider the sum of the anti-diagonals. Again, with suitable signs. And then you define H and the RAM XD as the cohomology in degree n, well, hypercohomology if you want, of the total complex of this double complex. And well, in principle, a cohomology class here is something complicated where you need to give an element in each term. But you can prove that they are actually always represented by a cohomology class on X. Okay, so in principle, for example, if D is really smooth, a class here is in principle represented by something like this. It's a pair omega eta, where omega is a differential on X of degree n, and eta is a primitive of the restriction of the derivative of the restriction of omega to D. So it means D eta is equal to omega restricted to D. Okay. And well, in general, it's more complicated. And out of this, you can get an exact sequence of the same shape. So have the cohomology of X, restriction to the cohomology of D. And here it comes the relative cohomology. Okay. And then I guess the claim is that if, the comparison isomorphism extends to these relative cohomology groups. And if you, yes. Yeah, I said that these classes are actually always represented by a class on X. You don't need to consider anything on. Yeah. Yeah. And yes. Maybe say it like this is not literally true. Probably not. No, yes, I think it's true that this class will always be the class of some other omega 0. Yes, but it's not obvious. It's something you need to prove. Sorry, these are the irreducible components. So you write D as a union of irreducible components, and the definition is made for this to be smooth separatities. And then you take all possible intersections. Okay, so now I would have done an example in detail, but I really want to tell you what comes after. So let me give the example as an exercise. So the exercise is compute the period matrix of H1 of the variety GM, so the affine line minus the origin, and relative to the union of 2 points 1 and t. And with t is a non-zero rational number, for example. Let's say positive rational number. Okay, and here you will find the logarithm. Okay, so now I'm going to state the Kontsevich-Zagier conjecture, which, as we will see, is essentially equivalent to the conjecture by Grothendieck that we saw in Bruno's lecture. So I will explain tomorrow how these 2 points of view are related. And this is a very wild conjecture that predicts all algebraic relations between periods of all algebraic varieties and relative to all subvarieties. And one way to formulate it is the following. So consider, so P is going to be the Q vector space generated by the following symbols: H, N, X, D, omega, sigma, where X is it's an affine variety, affine smooth. D is a simple normal crossing divisor. Omega is at the RAM cohomology class. And sigma is a Betty homology class. Omega is a class in the RAM. Sigma is a class in Betty. Okay, so this is, well, more or less like a period, except that a period is a number, and then this is a formal symbol. So you can go from this to I will leave some space here. So you can go from this to complex numbers computing the integral. Okay, you send such a triple to the integral of omega along sigma. So this map is not injective because there are algebraic relations between periods. So the goal of the conjecture is to describe the kernel. So you consider the vector space generated by these symbols, but you mod out but 3 relations. So modulo in the first component. Yeah, no, this is just a way to remember where the form lives. I'm going to give you relations. So the relations will involve forms living on different varieties. So this is to remember where you are considering your integrals. Well, so first relation is that this is bilinear on omega and sigma. Second relation is change of variables. So remember that the algebraic form of this was the functoriality of the comparison isomorphism. So it means if you have f from x to x prime that sends d to d prime, then you get you can do pullback. So the cohomology of x d pullback of omega sigma. So this is the same thing as h and x prime d prime omega f lower star sigma. Okay, so this is just the change of variables on the integral. And then there's a third relation that is Stokes formula. Well, you need to be a bit careful how you write this. So essentially, you want to relate the integral of d omega on sigma to the integral of omega on the boundary of sigma. So one way to do this is to go from x d and then d omega sigma to h n minus 1, the union of the irreducible components of d, the disjoint union, relative to the disjoint union of the intersection of two components. And here you put omega and delta sigma. Okay. So it's just Stokes formula. You need to be a bit careful with the smoothness of where you are considering the integrals. Because I want it to be smooth. In my generators, I'm considering a smooth variety. Nothing of this is necessary. I'm just trying to use what I explained. You could consider there are more sophisticated ways where you don't need this, but this should already be enough. And then the statement of the conjecture is that if you quotient by these three relations, then the map is injective. Okay, so injective. Okay. So in other words, every algebraic relation between periods comes from a combination of additivity, bilinearity of the integral, change of variables, and Stokes formula. Okay. An important remark here is that you see all these relations are linear, actually of the form a number is equal to another number. But out of this, you get polynomial relations because you can take tensor products. So if you have two periods and then you realize them on two cohomology groups, then the product of these periods will be a period of another cohomology group, which is cut out of the QNet formula. So this looks very linear, but it actually creates all algebraic relations between periods. Okay. And then more or less the only thing we know about this conjecture is a theorem that in this form is quite recent and is due to Huber and Birstolz, that says that this conjecture is true for linear relations between periods of curves. Okay, so linear means linear, and periods of curves means that in this conjecture you restrict to the case where x is of dimension at most 1. Okay, so you consider hn xd, and dimension of d is at most 1. Okay. And the reason why I did this remark is that now it is not true that linear relations imply polynomial relations, because when you consider the tensor product of cohomology of curves, you need something higher dimensional to realize this tensor product. Okay, so this doesn't give all algebraic relations, but it's already a lot. And yes, yeah, I'm going to give a very short indication. So the main ingredient here is something called Bristol's analytic subgroup theorem. Which is the following statement. So you take an algebraic group defined over Q bar. And well, this means commutative, connected algebraic group over Q bar. And then you consider its Lie algebra. So this is a vector space over Q bar. And if you tensor by C, you have a map to the complex points of the group, which is the exponential. Okay. So in the case where your group is GM, this is literally the exponential function. And in general, it depends on the group. So for GA is the identity. For an elliptic curve is a quotient from C to the quotient by the lattice, and so on. And then you assume that you have a point. So you assume you have a point U in G tensor C, such that the exponential of this point, so it is a priori a complex point of your group, it's actually an algebraic point. So it lies in Q bar. So Q bar is the physical Q bar, is the algebraic numbers inside C. And then you consider H, the smallest Q bar vector size space of G, such that U belongs to H tensor C. Okay. So now a statement of the theorem. This H is the Lie algebra of a subgroup. So H is the Lie algebra of some H, and H is a subgroup of G, an algebraic subgroup defined over Q bar. Okay, so this is the main ingredient in the proof. I want to give a feeling of how should this enter the proof, how this could enter the proof. Can this wait 5 minutes? So I finish and then you ask. So I was going to give 2 examples. So the first one is easier. So I will give you this example as an exercise. So use this theorem to prove that if alpha is a non-zero algebraic number, then exponential of alpha is transcendental. Okay, so this is a consequence of the theorem. You should apply it to the product of GA, the additive group, and GM. Okay, and what I want to explain quickly is something we saw in Bruno's lecture, is that if you have an elliptic curve over Q bar, and you consider the quotient of 2 periods of the holomorphic differential. So you consider a basis of homology, and you choose a generator of holomorphic differentials. Then this is algebraic if and only if the curve E has complex multiplication. Well, this is a theorem of Schneider from the 30s, so it's much older than Bristol's theorem, which is from the end of the 80s, but it's now a very striking consequence. So this implication is not hard because this is a tau that uniformizes the lattice. So if you have this, then the curve will be C quotient Z plus Z tau. And you know that for elliptic curves with complex multiplication, tau is an imaginary quadratic. So this is not hard to see. So the content is the other implication. And for this, you do the following. So you consider as your group the product of two copies of E. Then the Lie algebra tensor C is two copies of C. And then they said you can consider this uniformization by the period lattice. So this will be C quotient lambda times C quotient lambda. And the exponential in this case is the quotient map. Okay, so for example, you get, how do you get a point in the algebraic points of the group? But you can take two periods. So this is a point whose exponential is an algebraic point because it is equal to 0, the origin in the group. Okay, so we need to, let's assume alpha tau is algebraic. So if tau is algebraic, then we can describe this H. So the smallest Q vector subspace that contains this point. So what it is the set of ZW such that Z is tau times W. Okay, so since tau is algebraic, then this is defined over Q bar. So this will be H, and so defined over Q bar. And then the theorem says that this is the Lie algebra of a subgroup of E times C defined over Q bar. But well, there are not so many subgroups of a product of an elliptic curve with itself. So now you just need to analyze a little bit the situation. So you have H inside E times C. You can consider the projections to the two coordinates. And none of this projection is the zero map because well, you have the periods on its component and the periods are non-zero. So this means that each of these projections is a finite map. So then you can compose P2 with the inverse of P1, so P1 divided by the degree. And then this will give an endomorphism of the elliptic curve tensor Q. Okay, tensor Q, but because probably you need to divide by the degree. And you know that this is either the integers or an imaginary quadratic field. But it cannot be the integers because you know what this does on the tangent space, for example, and on the tangent space is multiplication by tau. So this means that there is something, this is strictly bigger than Q. And this is what it means that the elliptic curve has complex multiplication. Okay, thank you. Please. Mm-hmm. No, you consider all the relations, and what the theorem says that you take any two complex numbers that are obtained as a period integral on a curve, and well, on a curve or something that looks like a curve. It could be an abelian variety, for example, but let's say on a curve, and you assume that there's a linear relation between these two periods. Okay, so it means that this easiest case, these two periods are equal, two very different integral representations of the same period. So the theorem says that you can go from one integral representation to another using just, well, bilinearity of the integral, change of variables, and Stokes formula. So that's what it says. And I'm going to use this conjecture tomorrow as a motivation to construct the motivic Galois group. So even if the conjecture is not true or we don't know how to prove it, you can use it as a motivation to give an unconditional construction of the motivic Galois group. Yes. Well, there's yeah. If you just have the yeah, I guess no, because no. If you know some description of the number, like it is given by a sum of some infinite series, or is a special value of a function, or there I think you have good chances to, well, either to prove it is a period or to get like a common sense explanation that is not going to be a period. But if you just know it numerically, I guess no. Yeah, so you can, there is a result that says that periods form a set of computable numbers in some precise way. So then you can describe an algorithm that writes down a number which is not computable, so it is not going to be a period. But well, this is, I mean, it is a number, but with my definition of numbers, well, it's not something that you can describe by one of these methods, an integral or a series or a special value of something. So this is one way to think about the question. There are numbers like E or values of the Bessel functions or Euler's gamma constant, these kind of things, which are exponential periods, but not periods. And you can prove that if you assume some conjecture in the style of the Kontsevich-Zagier conjecture, then they are not periods, but they are still very close to, and yeah, you know, periods should have very special properties, like the irrationality measure or transcendence measure should be equal to 2. I mean, it's impossible to prove that something is not a period. Yes.
I think it's I mean, isn't the you can also write down a computable number which is not a period, right? To any degree of accuracy.
Yes, you can do that, yeah.
And sorry, and one other, like, you remark you made, like if it's either a curve or an abelian variety, what do you mean by that? Like you said that the theorem holds even if it's an abelian variety.
Yeah, I'm just saying that it's a bit similar, like in Bruno's course, where he has these things of level 1 that sometimes they are not abelian varieties, but they can be constructed from abelian varieties by some geometric operation. So for example, if you want to study periods of abelian varieties, I don't know, you can take a curve inside the variety and work with this curve, and then try to relate your variety with the Jacobian of the curve, and then the H1 of the Jacobian is the same as the H1 of the curve. So it's more a question of the degree, the cohomological degree is 1. You shouldn't focus too much on the dimension of X, but it's more the cohomological degree of the period.
When you say cohomological degree, you mean like H1?
H1, yeah. Like that you are working with an H1. Precisely, you can prove that the set of periods that you obtain from H1 of all varieties is equal to the set of periods you obtain from H1 of curves. This is what you can prove.
In that theorem, when the axiom about the Stokes formula does involve also variety of higher dimension or just curve and point?
No, yes, curves and points. Yeah. You could imagine something more complicated, but that's another one there.
Yeah, could you maybe quickly repeat the conclusion at the end about why this elliptic curve has complex multiplication?
Yeah, sure. So I use the theorem to produce this subgroup inside the E times E, and then I'm trying to argue that well, first of all, that this is not E times 0 or 0 times E, but that it is the graph of an endomorphism of the elliptic curve. And then it could be the graph of multiplication by some integer, and then we gain nothing. But if you look the way H is constructed, so H is the exponential of H, so it means that you can really compute the differential of this endomorphism, and the differential will be tau. And tau, well, tau was the quotient of the two pairs, and you know it is not an integer. So in this way, you see that there is really some extra endomorphisms. Thank you. Yeah, so this is just I just wanted to give an idea of how this theorem could imply some transcendence property of periods, and then it is a lot of work to get the theorem from that, but you know, that's somehow the main ingredient.
Are there other questions? Okay, if not, we can thank Javier again.
Thank you.